Hello there, and welcome to Science for Sleep, the quiet corner where the universe slows down just enough for your mind to wander without hurry. Tonight, we're going back to the very beginning. Not the beginning of life, or of Earth, or even of the stars above your head. We're tracing everything back as far as we can, to the moment when reality itself came into being, or at least to the closest point our understanding allows us to reach, before it fades into the kind of silence that even mathematics can't break. But before we do, I'd like to ask you something simple. Where are you listening from right now? Are you curled up under a blanket while the world outside has gone quiet? Or are you somewhere with a little background hum of life, like distant traffic or the soft ticking of a clock? Whatever time it is where you are, I'm glad you're here, because tonight's question isn't just about science. It's about that deep, strange human urge to look up at the sky and wonder how all of this began. And if you find that kind of wondering as comforting as I do, I'd be grateful if you gave this a like, maybe even subscribed, so we can keep exploring together. There's something soothing about knowing you're not the only one awake at this hour, staring into the dark and thinking about the brightest thing of all, the beginning of everything. Now, let's ease ourselves into this. No rush. After all, we're about to talk about time before time, space before space, and what it means to even say there was a before. It's one of those questions that never quite sits still. How did the universe start? Every time you think you've reached an answer, the question seems to slip just a little further away, as if the universe enjoys keeping a few secrets tucked out of reach. And yet, bit by bit, we've managed to peel back the layers, to see further into the past than any of our ancestors could have dreamed. The most astonishing thing is that the story of the universe doesn't begin with stars or galaxies or even light. In fact, it begins in a way that defies our usual way of thinking. Imagine everything you've ever known. Every grain of sand, every breath of air, every spark of thought, compressed down into a point smaller than anything you could picture. Not just matter, not just energy, but space itself, time itself, all wrapped up in an unimaginably dense, hot state. It didn't sit there for long. Whatever it was, however it happened, it didn't stay still. It expanded, it roared outward, and in less than the blink of an eye, it was no longer a point, but universe in motion. That moment is what we call the Big Bang. Though the name is misleading, because it wasn't a bang in the way we normally imagine. There was no sound, because there was no air to carry it. There was no explosion flinging matter into empty space, because space itself was expanding along with it. And yet, as strange as it sounds, that's the point where our story begins. We don't know what came before, or even if before is a meaningful word in this context. We only know that from this single, impossible beginning, everything else followed. But what's remarkable is that we've been able to find evidence of that beginning still echoing around us. Quiet but unmistakable, like the fading sound of a bell that was struck almost 14 billion years ago. Before we get to that evidence, though, think about what it means to even try to picture those first moments. The temperatures were so high that matter as we know it couldn't exist. Particles were whirling around in a dense, chaotic soup, colliding, annihilating, forming again, breaking apart. Space itself was stretching faster than light could travel across it. That early inflationary burst took what was once unimaginably small and blew it up to cosmic scales in a fraction of a second. And in that expansion, the seeds for everything, every star, every galaxy, every world were planted, though at the time they were nothing more than tiny ripples, minuscule fluctuations in density that one day would become the structure of the universe we see now. It's almost funny when you think about it. The vast beauty of the night sky, all of it, began as something you could not see or touch. It was all potential, all raw possibility waiting to unfold. And if we could somehow watch it happen, frame by frame, we wouldn't have seen galaxies swirling into existence right away. We'd have seen nothing but an ocean of energy, a brilliant fog of particles that didn't yet know they were supposed to become stars. But here's the thing. As alien as it all sounds, that early universe left fingerprints we can still study. We can see the afterglow of those first moments in the cosmic microwave background radiation. A faint wash of light stretched and cooled over billions of years, now so weak it's invisible to our eyes, but still detectable with the right instruments. It's like an ancient photograph of the universe, when it was only a few 100,000 years old, long before the first stars lit up. And from that faint afterglow, we've learned something astonishing. We've learned that the universe didn't just happen. It followed patterns, rules, rhythms. Those tiny fluctuations in the early plasma grew, guided by gravity, into the cosmic web we live in today. Every galaxy we see in the sky, every star that burns, every atom in your body, each of them traces back to those minute variations from the very beginning. It's humbling, isn't it? The idea that the universe began with such extreme simplicity, and yet carried within it the blueprint for everything to come. Of course, the story doesn't stop there. Once the universe cooled enough for matter to take shape, things began to change. Hydrogen and helium, the simplest elements, formed out of the primordial fire. They were nothing special on their own, just basic building blocks. But under the pull of gravity, they gathered together, clumped and collapsed. And in those dense knots of matter, the first stars were born. Those stars were enormous compared to the ones we see today, blazing fiercely and living fast. They burned through their fuel quickly and died spectacularly, exploding as supernovae that scattered heavier elements into the cosmos, carbon, oxygen, iron, the ingredients that much later would make planets, and eventually us. But even as the first stars burned, the universe around them kept expanding. Space stretched, galaxies formed, and clusters of galaxies began to weave themselves into an immense cosmic web. And all the while, that expansion never stopped. In fact, it was only in the last few decades that we discovered it wasn't just expanding, it was accelerating, driven by something we call dark energy, a force we still barely understand. And that discovery, in its own way, loops us back to the beginning. Because if we want to understand why the universe is expanding faster today, we need to understand what set it in motion in the first place. And that brings us back to that first question, the one that lingers no matter how many answers we stack on top of it. What was there before all this? Was there a before? Or is time itself something that only began with the universe? Some physicists suggest that the question doesn't even make sense. That talking about before the universe is like asking what's north of the North Pole. Others argue there may have been something, some previous state, perhaps a universe before ours that collapsed and rebounded, or a quantum field simmering with fluctuations from which our universe emerged. We don't know, and maybe we never will. But what we do know is that from the very instant this universe began, everything that would ever be was set on its path. And even though we've given it a name, the Big Bang, that name only hints at the enormity of what happened. It was not just an event in time. It was the beginning of time. It was not just something that happened in space. It was the beginning of space. And even now, when we look deep into the night sky, we are looking back at that beginning, because the light from the most distant galaxies has been travelling toward us for billions of years. When we catch it, we are literally seeing ancient history, written in photons. So here we are, floating in the present, tracing the faint echoes of that unimaginable start. And if you let yourself sit with that thought for a moment, you might feel a strange kind of quiet comfort in it. Because even though the universe began with an event so violent and so absolute that we can barely comprehend it, what it gave rise to was this: a night sky filled with stars, a world where life can exist, and this exact moment in which you're listening now, wondering about it all. And that, in its own way, might be the most extraordinary thing of all. And from here, it only gets stranger, because if we follow this thread a little further, we start to uncover what those first fractions of a second really looked like, and what they can tell us about the hidden structure of reality itself. When you trace the story of the universe back to its very first flicker of existence, it has a way of leaving you with more questions than answers. For all the progress we've made, for every telescope and particle accelerator that's helped us peel back another layer, there's still that one question that refuses to leave quietly. It sits there, right at the edge of everything we know, like a single light that never goes out. Why did any of this happen at all? It's the kind of question that sounds simple until you try to answer it. Because the moment you ask, you find yourself falling into a chain of whys that just keeps going. Why is there something instead of nothing? Why did this universe, of all the universes that could exist, begin in exactly this way? Why does the fabric of reality have rules that allow stars and planets, and eventually us? It's a question that feels older than science itself, older than language even. The kind of thing our distant ancestors must have wondered when they first looked up at a night sky so dense with stars it must have felt almost overwhelming. And even now, with all our equations and maps of the cosmos, the question hasn't gone away. If anything, the more we learn, the louder it gets. We know about the Big Bang, we know about cosmic inflation, about the early plasma, about how the first particles came together to form the raw material of everything. But none of that answers the deeper, quieter question lurking underneath. All of those discoveries are about what happened after the universe began. They don't explain why it began. Some physicists would say that why is the wrong way to think about it. They'd say there doesn't have to be a reason. The universe is here simply because it can be. According to some interpretations of quantum mechanics, universes can pop into existence out of quantum fluctuations, little bubbles of space-time emerging from what we'd call nothing. Although even that nothing isn't truly nothing. It's a seething, restless sea of possibility where space and time as we know them don't exist. Only probabilities and raw potential. But the idea that our universe could just appear like that, without a cause, without a before, is something our minds resist. We're wired to expect causes. We're used to one thing leading to another. An acorn grows into an oak tree. Rain fills a river. Fire burns until there's nothing left to burn. We live in a world of sequences, so it feels almost impossible to picture something that doesn't begin with a before. And yet, when we push physics all the way back to the start, to the moment time itself seems to have begun, that's exactly what we run into. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. And maybe that's why this question has such staying power. Because even when we build models that explain almost everything, there's always a point where the math goes silent. We can describe how the universe evolved from its first instant onward, but not what lit the spark in the first place. What's fascinating, though, is how much that single unanswered question has driven us forward. It's why ancient astronomers built stone calendars to track the motions of the heavens. It's why philosophers argued over whether the universe had a beginning or had always existed. It's why scientists like Georges Lemaitre and Edwin Hubble kept following the evidence no matter how strange it became, until we learned that space itself is stretching, and the cosmos is not eternal but had an origin. And yet, even with the Big Bang model in hand, the question only changed shape. Instead of asking whether the universe had a beginning, we now ask what that beginning really was. Was it truly a singularity, a single point of infinite density and heat, where all the laws of physics broke down? Or is that just a placeholder for something deeper we haven't yet discovered, some new physics that will rewrite our understanding of the first moments? When we look at the cosmic microwave background, the afterglow of the early universe, it's almost like staring at a photograph from just after everything began. Those faint ripples of temperature across the sky aren't just random noise. They're the frozen imprints of the very first fluctuations that grew into galaxies. It's a snapshot of the universe when it was only 380,000 years old, still glowing from its birth, still settling into its own shape. And as beautiful as it is, it also carries with it that stubborn question, because it shows us how the universe evolved, but not why it was there to evolve in the first place. Even when we try to imagine other possibilities, we find ourselves looping back to the same point. Maybe our universe was born from the collapse of a previous one, in a cycle of endless expansion and rebirth. Maybe there are countless universes, each with their own laws of physics, endlessly bubbling into existence in a vast multiverse, and we just happen to live in one that works. Or maybe, as some theories suggest, there's no real before, because time itself began with the universe. And asking what came before it is like asking what's north of the North Pole. Each of those ideas sounds strange in its own way, and yet they all exist because of that single unshakable question. We don't stop asking it because it refuses to stay answered, and maybe that's the point. Maybe it's not a question you solve once and for all. Maybe it's a question that exists to keep us looking, to keep us turning the universe over and over in our hands, examining every angle, never quite satisfied but never quite able to let it go either. And it's not just a scientific question, is it? It's the kind of thing that follows you into the quiet hours of the night, when the noise of the day fades and you're left with only the hum of your own thoughts. You don't need to know the math or the physics to feel it. All you have to do is look at the sky, or even just close your eyes and imagine the darkness behind it, and wonder what it was like when the first spark of existence lit up the void. That's what makes this question so strange and so enduring. It doesn't matter how many answers we build. It always feels personal. You can be sitting in a room, 1 billion miles from the nearest star, and still feel it pressing at the edge of your mind. The same way our ancestors must have when they first noticed the sky wasn't just a ceiling, but something deeper and endless. And so, the question stays. Not as a frustration, but as a kind of invitation. Because every time we ask it, we're pushed a little closer to the edge of what we know, and every step we take into that unknown has a way of reshaping everything behind it. The question doesn't just sit there, it leads. And if we follow it far enough, if we let it pull us right to the threshold of the beginning, we start to glimpse something even stranger than the question itself. We start to see that the story of how the universe started is not just about that first instant. It's about what came immediately after, in a fraction of a second so brief it almost feels impossible that anything could happen at all. And yet, in that instant, everything we now see was set into motion. And that is where the story turns, from the silence of why to the roaring, incomprehensible birth of how. If there's one idea that pushes our minds further than almost any other, it's this. Before the Big Bang, there was nothing. Not the kind of nothing you find in an empty room, not the quiet space between the stars, but a nothing so complete it almost defies the ability to imagine it. No space, no time, no matter, no energy, nothing to measure, nothing to see, nothing even to ask a question about. And yet somehow, out of that absence, everything began. The trouble with this idea is that our brains aren't built for it. When we say nothing, we usually mean empty. An empty glass, an empty street, an empty box. All of these still exist in space and time. They still have a shape, a location, a presence we can point to. True nothingness is different. It's not just empty, it's the absence of the very stage on which anything could exist at all. And that's where the story of the universe forces us into a kind of paradox, because when we push back far enough, we run out of room for even the word before. You see, in our ordinary lives, time is what allows us to tell a story. First this happens, then that. One thing leads to another. But if time itself was born with the universe, then the phrase "before the Big Bang" is meaningless. There was no before, because before requires time, and time didn't exist yet. It's a little like asking what's above the top of the sky. There isn't an above, you've simply reached the edge of what the word can describe. And yet scientists and philosophers keep circling this void, not because they expect to find something simple hiding there, but because every step toward it seems to reveal another layer of how strange the beginning truly was. One of the leading ideas is that what we call nothing isn't really nothing at all. In the world of quantum mechanics, empty space isn't empty. It's a restless sea of energy, with tiny fluctuations popping in and out of existence, virtual particles flickering briefly into being before vanishing again. It's sometimes called the quantum vacuum, and while it's nothing like the solid world we know, it might be the closest thing we have to a foundation for existence. In this view, the universe didn't erupt out of absolute nothing. It emerged from this underlying quantum foam, a place where the laws of physics themselves are blurry, and where, given enough time, or perhaps outside of time entirely, a fluctuation big enough could ignite reality as we know it. It's not a comfortable thought. We like to picture beginnings as tidy, as something that happens on a clear stage with a clear cause. But in this picture, the universe could have begun the way a ripple appears on a still pond, except there was no pond and no stillness, just potential. And that raises another possibility, one that has fascinated scientists for decades. Maybe our universe is not alone. If quantum fluctuations can give birth to one universe, why not many? Perhaps the cosmos is far larger than we can see, an endless expanse of bubbling universes, each one with its own laws of physics, each one flickering into being the way ours did. In that case, what we call the universe would be just one pocket in an infinite sea of beginnings. It wouldn't answer the question of why there is something instead of nothing, but it would shift the question into a new and stranger form. Why this universe and not another? Some physicists go even further and suggest that nothingness is not a single state, but a kind of illusion. They argue that the universe may be eternal in some sense, not in time as we know it, but in a deeper, more fundamental way, with the Big Bang simply marking the point where it became something we could describe. Others imagine cycles of expansion and collapse, where each universe gives birth to the next in an endless loop, with no ultimate beginning and no final end, only transformation after transformation. But for all those theories, we always end up circling back to the same boundary. No matter how far we reach, there's a horizon we can't cross, a point where our equations falter and our words stop working. That horizon is what we call the Planck time, a vanishingly small fraction of a second after the Big Bang, 1/10 million trillion trillionth of a second, beyond which our current physics can't see. Before that instant, everything we know about space, time and matter loses meaning. The universe wasn't simply hot and dense. It was something else entirely, a state so extreme that our laws of nature, the very ones we rely on to make sense of anything at all, simply dissolve. This is why, even though we speak of the Big Bang as a beginning, we should be careful about what we mean. The Big Bang isn't so much the moment of creation itself as it is the earliest point we can meaningfully describe. Whatever came before, if before even applies, remains hidden behind a wall we don't yet know how to climb. And yet, that hasn't stopped us from trying. Consider this. When we look deep into space, we are also looking deep into time. Every photon that strikes a telescope lens has been travelling for billions of years, carrying with it a story written at the dawn of everything. And the deeper we look, the closer we get to that wall, that limit where the universe was still opaque, still so dense with heat and light that nothing we recognise could exist. That wall doesn't feel like an ending. It feels like a signpost. It's the universe's way of telling us that there's something beyond it, something we haven't yet learned how to see, and perhaps that's the real weight of the question. Before the Bang isn't just about the literal beginning, it's about the limits of our understanding and the way the universe keeps daring us to push them. It's about a kind of nothingness that isn't empty, a silence that isn't quiet, and a mystery that isn't waiting to be solved so much as it's waiting to be lived with. Because even if we never answer the question in full, even if the nature of before remains forever hidden, that mystery is what has carried us this far. It's why we build bigger telescopes, why we smash particles together at near light speed, why we stare at the sky long after the practical questions have been answered. We're not just trying to know how it all began, we're trying to see how far the question itself can take us. And so, when we speak of nothing, Maybe what we're really talking about is the place where all beginnings hide. Not empty space, not void, but the raw potential that, for reasons we may never entirely understand, became this: stars, galaxies, planets, and a small world where, somehow, there are people who stay up late wondering about it all. And from that unfathomable nothing, from that invisible threshold, came the first instant of everything. And that is where we now turn, into the fraction of a second when the universe erupted from silence and began to write the first line of its story. From that impossible nothing, there came a moment when everything began. It didn't begin with sound, because there was no air to carry it. It didn't begin with light either, not in the way we see it now. It was simpler, or a stranger, a spark in the dark. Not so much a flash, as an unfathomable surge. One instant there was no universe at all, and the next there was a storm of existence expanding in every direction at once. If you could somehow watch it unfold, you wouldn't have seen stars or galaxies. Those were far in the future. What you would have seen, if seeing was even possible, was an ocean of pure energy, a furnace so hot and so dense that the idea of matter as we know it simply didn't exist. Time itself had only just begun ticking, and space was stretching so quickly that distances doubled in less than the blink of an eye. This wasn't ordinary expansion. This was inflation, an unimaginably brief and violent growth spurt that took the universe from something smaller than an atom to something vast enough to lay the foundations for everything we know today. It's almost impossible to wrap your head around, because nothing in our daily lives moves this way. Inflation didn't just happen fast. It happened so fast that the word fast barely applies. In a fraction of a second, the universe grew by an amount so staggering that if it had kept going at that rate, the night sky would have been empty, swept too thin for stars to ever form. But it didn't. Like a hell breath slowly let out, that first expansion slowed, and in the slowing, the chaos began to settle. Energy cooled, just enough to start changing form. Particles began to appear, tiny, fundamental pieces of reality, the building blocks of everything that would one day exist. At first they flickered in and out of existence, colliding, annihilating, reappearing, an endless dance of creation and destruction. Quarks, electrons, and other ghostly particles filled the newborn universe, carried along by the wild expansion of space. And with every fraction of a second as the heat dropped, the universe grew just a little more orderly. It wasn't peaceful, not yet. This was a cosmos still in its first heartbeat, a churning fire where forces that would one day shape galaxies were only just finding their strength. Gravity, that quiet sculptor of worlds, was already at work, pulling against the expansion, trying to weave structure out of the chaos. The strong nuclear force bound quarks together into protons and neutrons. The electromagnetic force crackled invisibly, a thread that would one day tie atoms together, and beneath it all, the weak nuclear force quietly governed the balance between matter and its mirror image, antimatter, in a way that would decide the fate of the universe itself. Because here's the thing. In those first fleeting moments, matter and antimatter were born in nearly equal amounts. For every particle there was its opposite, its mirror, its undoing. When they met, they annihilated each other in brilliant flashes of pure energy. By all rights, this cosmic duel should have ended in perfect balance, a universe of light but no matter at all. And yet somehow, for reasons still not fully understood, matter won. By the tiniest margin, a handful of particles escaped annihilation, and those survivors, those few lucky scraps of matter, became the raw material for everything. Stars, planets, and eventually the atoms in your body. It's strange to think how much the universe turned on such a small difference. If matter and antimatter had been created in perfect symmetry, there would be nothing here to wonder about it. No stars to shine, no worlds to hold, oceans and mountains, No minds to look back and trace their origins. That infinitesimal imbalance was enough to tip the scales and turn chaos into a future. As the universe kept expanding and cooling, those surviving particles began to settle into new forms. Protons and neutrons clumped together, binding into the first atomic nuclei. This was the era of nucleosynthesis, when the first ingredients of the cosmos were written into being: hydrogen, helium, and traces of lithium, forged in the searing heat while the universe was still impossibly young. They were simple elements, but simplicity was exactly what was needed. These were the seeds. The universe didn't need complexity yet. It needed a foundation, and then for a while nothing dramatic happened. The universe just expanded. It stretched and thinned and cooled. For hundreds of thousands of years it was still a glowing fog, too hot for atoms to hold onto their electrons. Light couldn't travel freely. Everything was trapped in a blinding haze. But that haze carried with it the faintest ripples, tiny imperfections in density, born out of the quantum fluctuations from the very first instant of inflation. And it was those ripples, so slight and so small that they seemed meaningless, that would eventually grow into everything. It's humbling, isn't it? To think that galaxies, clusters, superclusters, the entire grand architecture of the cosmos, all of it, was encoded in those first delicate variations. Without them, the universe would have been perfectly smooth, and in a perfectly smooth universe, nothing ever condenses. No stars ever light up, no planets ever form. But the universe was never perfectly smooth. It was uneven, imperfect, and that imperfection was the greatest gift of all. Eventually, as the universe cooled further, it reached a point where the fog began to clear. Electrons finally bound themselves to nuclei, and the first true atoms were born. Light, for the first time, was free to travel, no longer trapped in the dense plasma of the early universe. That light is still out there today, stretched thin by billions of years of expansion. We call it the cosmic microwave background, a faint whisper from the birth of everything, still glowing softly in every direction, a relic of that spark in the dark. And here's the quiet, almost poetic thing about it. When we study that light, we are looking directly at the universe as it was just after it emerged from its earliest chaos. It's the closest thing we have to a window into the moment everything began, a photograph taken before there were stars, before there were galaxies, before there was anything but the raw potential for what was to come. And yet, for all the clarity this gives us, there's something about it that only deepens the mystery. Because even if we can trace that spark, even if we can follow it through inflation, through particles and nuclei in the first atoms, there's still that haunting question sitting just beyond reach. What lit the spark in the first place? What set the stage for a universe where anything at all could happen? Some say the answer is simply that it happened because it could. In a quantum reality, fluctuations are inevitable, and given enough time, though the word hardly applies, one of those fluctuations was bound to bloom into a universe like ours. Others argue that perhaps the spark was never lit at all, because there was never a moment of true nothingness to begin with, only an eternal something, changing its form over and over, and the Big Bang was merely the latest transformation in a story without a first page. We don't know which, if any, of these ideas is true, but we do know that whatever the answer is, it left behind a universe that didn't remain a chaotic furnace forever. It cooled, it expanded, it formed atoms, and in the quiet after that first violent flash, it began preparing for what would come next. The fog would thin, darkness would fall, and in that darkness the first stars would be born, tiny points of light igniting against the infinite night, carrying the universe into its next great chapter. But before those stars could shine, the cosmos would have to pass through its longest, quietest era, the age of darkness, when the spark of creation had already happened, but the universe was still waiting for its lights to turn on. And that is where the story leads next, into a silence that would last for hundreds of millions of years, until the first brilliance broke through. If there was ever a moment when the universe seemed impatient, it was in those first, almost impossible instants. Because after that first spark, reality didn't just unfold at a steady pace, it raced. It's a strange thing to picture, this sudden, staggering acceleration. But it was during this briefest fraction of a second that the universe grew from smaller than a single atom to something vast enough to hold everything we now see in the night sky. This was inflation, a period so brief and so violent that it almost feels unreal, and yet it is one of the best supported ideas in modern cosmology. To understand it, imagine space itself as a kind of fabric. In the earliest moment of the universe, that fabric didn't simply stretch. It ballooned outward, doubling again and again in a time so short it makes every ordinary measure meaningless. In less than a heartbeat, what had once been unimaginably tiny became the size of a galaxy. And yet, this wasn't an explosion in space. It was space. That's the part that's hardest to grasp. Nothing was moving through anything else. The universe itself was swelling, and every point within it was carried along. Why did this happen? The simplest answer is that the universe was born with energy locked into its very fabric, a kind of vacuum energy that drove this runaway expansion. We don't know why that energy existed, only that for a fleeting instant it dominated everything. And then, just as abruptly as it began, it ended. Inflation switched off, like a storm passing, and all the energy that had driven it was released in a burst of heat and matter. In that single step, the foundations of the universe as we know it were set. It's almost absurd how fast this all was. Inflation is thought to have lasted only a fraction of a second, far shorter than the time it takes you to blink. And yet, in that tiny span, it solves some of the biggest puzzles about why the universe looks the way it does. Without inflation, the cosmos should be uneven and lumpy, full of jagged differences in temperature and density. But when we look at the cosmic microwave background, the faint afterglow of the early universe, we see something astonishing. It's almost perfectly smooth, with only the tiniest ripples scattered across it. Inflation explains why. By stretching the universe so quickly, it ironed out any irregularities, spreading everything so thin that what remained was nearly uniform. And yet those tiny ripples, the ones that inflation left behind, were just enough to become the seeds of every galaxy. They were small quantum fluctuations, minuscule variations that existed in the strange, uncertain world of the very early universe. Inflation took those fluctuations, invisible and meaningless on their own, and stretched them to cosmic size. They became the blueprint for structure, the reason why matter didn't stay evenly spread forever, why gravity eventually had something to grab onto. Without inflation, there would be no stars, no planets, nothing but a smooth, empty void. It's one of those ideas that sounds so bizarre you almost want to doubt it, but the evidence for inflation is written across the sky. The pattern of those tiny temperature ripples in the cosmic microwave background matches exactly what inflation predicts. Even the vast scale of the universe itself, far larger than it could have become through normal expansion alone, is what you'd expect if inflation happened. Every time we build a better telescope, every time we sharpen the map of that ancient light, we see the same thing, traces of a universe that, for a brief moment, outran everything. But perhaps the strangest part of inflation is not just what it explains, but what it implies. Because if space can expand like that once, who's to say it can't happen again? Some physicists believe inflation might be eternal, still happening even now in distant regions far beyond our view. In this picture, our universe would be only one bubble in a vast cosmic foam, each bubble a separate universe, born from its own burst of inflation, each with its own rules, its own story, its own beginning. If that's true, then the ultimate answer to the question of how the universe started might be that ours didn't begin in isolation at all. It was simply one more spark in an endless cosmic storm. Of course, we don't know if that's true. We may never know, because anything beyond our bubble would be forever out of reach. But it's a reminder that inflation isn't just a detail of the early universe. It might be the thing that connects our story to something unimaginably larger, a reality where our entire cosmos is just one of countless others, all born from the same strange runaway expansion. Even if we leave that possibility aside, though, the importance of inflation is clear. It didn't just make the universe bigger, it made it possible. By smoothing out space while leaving behind just enough imperfection to form stars and galaxies, it created the stage for everything that would follow. And when it ended, it handed the universe over to the slower, steadier kind of expansion we live with today. A universe no longer racing, but drifting, cooling, and beginning to take its first steps towards structure. What followed inflation was a period of intense transformation. The universe was still a furnace, but it was a furnace with rules now, a place where particles could form and survive, where forces began to settle into their familiar roles. Gravity, electromagnetism, and the nuclear forces separated from one another, each one becoming distinct, shaping matter in ways that would eventually give rise to atoms, stars, and everything else. But for all of that, the universe in those moments was still nothing like the one we know. It was a seething plasma of particles colliding and scattering, a cosmic soup that would take hundreds of thousands of years to cool enough for light itself to escape. It was a universe in waiting, full of potential but still shrouded in its own heat. Inflation had given it the size and the structure it needed, but the work of turning that raw, formless energy into the beginnings of a visible cosmos had only just begun. And that's the strange beauty of this story. Inflation, for all its unimaginable speed, wasn't the end of the beginning. It was merely the breath before the next step, because from here, the universe would slow down. It would cool. It would begin to take shape in ways that would set the stage for everything else. From the birth of the first particles to the quiet emergence of light after hundreds of thousands of years, the race had ended. The long, steady unfolding of the cosmos had begun. And now, if we follow that unfolding forward, we'll find ourselves drifting into a quieter moment, one where the chaos of inflation gives way to the first simple ingredients of reality, and the universe begins, for the very first time, to build. As the furious sprint of inflation slowed, the universe entered a different kind of moment. Not quiet, not calm, but no longer racing. It was still unimaginably hot, still so dense that nothing we would recognise could exist, and yet in that early fire the first true pieces of the cosmos were taking shape. This was the era of particles, the primordial soup from which everything would ultimately come. If you could have looked inside that newborn universe, you wouldn't have seen stars or galaxies. You wouldn't even have seen atoms. What you would have seen was chaos, a swirling plasma of particles and energy, colliding, vanishing and reappearing in a dance so rapid and so alien that even the word soup doesn't quite do it justice. It was matter and antimatter locked in a constant struggle, radiation flooding every corner, and forces still settling into the roles they would play for the rest of cosmic history. In those first millionths of a second, something remarkable happened. The fundamental forces of nature, which had once been united in that earliest, unknowable instant, began to separate. Gravity had already broken away during inflation, asserting itself as the slow, steady hand that would one day bind stars and galaxies together. Now, the strong nuclear force and the weak nuclear force began to split apart as well, followed by electromagnetism. Each of these forces would go on to shape the universe in its own way, gravity pulling matter into clumps, electromagnetism guiding the dance of charged particles, the nuclear forces forging the hearts of atoms. But here, in this primal soup, they were still freshly formed, still carving out the basic framework of reality. And then came the particles themselves. Out of that seething energy, quarks emerged, the tiniest known building blocks of matter. They didn't exist alone for long. The strong nuclear force bound them together into protons and neutrons, the cores of what would eventually become atoms. At the same time, electrons appeared, lighter and quicker, darting through the plasma like restless sparks. Alongside them came neutrinos, ghostly particles so elusive they could pass through entire planets without interacting with anything at all. These first moments were crowded, chaotic, and unimaginably small, and yet everything that would ever exist began here, in this dense, hot churn. But the universe had one more trick to play. For every particle of matter that formed, there was a matching particle of antimatter, a mirror image with the same mass but opposite charge. And when matter and antimatter met, they obliterated each other, vanishing in flashes of pure energy. For a time, this cosmic annihilation was almost total. The universe could easily have erased itself in that frenzy, leaving nothing but a bath of light. And yet, against all odds, matter won. Not by much, just the tiniest imbalance. Maybe one extra particle of matter for every billion pairs of matter and antimatter. But that sliver was enough. When the fury of annihilation finally passed, the few survivors of matter remained, scattered like embers after a great fire. Those particles, so few compared to the light still flooding the cosmos, were the foundation stones of everything to come. Every star, every planet, every living thing owes its existence to that small, improbable surplus. As the universe continued to expand, it cooled just enough for the next great transformation. Protons and neutrons, guided by the strong nuclear force, began to fuse together. This was nucleosynthesis, the first time the universe started to assemble elements. It was a brief but decisive moment, lasting only minutes, but in that short span, hydrogen and helium were born, along with a trace of lithium. These simple elements made up almost all of the matter in the early universe, and they would remain its dominant ingredients even after billions of years. Hydrogen, the simplest atom, was especially important. It would become the fuel of the first stars, the raw material from which nuclear fusion would ignite. Helium, forged in those same early moments, was the quiet companion, a reminder of the universe's fiery birth. And lithium, though rare, hinted at the precision of those first minutes. A balancing act so delicate that even the slightest difference would have left the cosmos looking utterly unlike the one we know. But even as these first elements formed, the universe was still too hot and dense for atoms to exist in any familiar sense. Electrons were not yet bound to nuclei. Instead, they roamed freely through the plasma, scattering light in every direction. To an outside observer, if such a thing could have existed, this early universe would have been blinding, a brilliant haze where nothing could travel far without colliding with something else. Yet even in that haze there were faint beginnings of structure. Quantum fluctuations from the earliest moments of inflation, those tiny random wrinkles in space-time, were still there, stretched to cosmic scales. They were almost imperceptible, but they mattered. Over time, gravity would use them as a blueprint, pulling matter toward those slightly denser regions, slowly gathering it into clumps that would one day grow into galaxies. In these first seconds and minutes, time had only just begun to unfold in a way we could measure, and yet the stage was already set. The forces of nature had taken their places. The first particles were born. The lightest elements had emerged. All of this happened in the briefest flash of cosmic history, and when it was done, the universe was still young, still impossibly hot, still wrapped in its blinding plasma, and then came the long wait. After those early minutes, nothing fundamentally new was created for a very long time. The universe simply expanded and cooled. It was a furnace in retreat, a cosmos slowly settling into itself, its particles drifting apart while light remained trapped, endlessly scattering in the glowing haze. For nearly 380,000 years, that was all the universe was. A brilliant, featureless plasma. No stars, no planets, no galaxies. Just a boundless, formless ocean of matter and radiation, cooling grain by grain, degree by degree, as space stretched ever wider. But this weight was not empty. In its quiet, the universe was preparing for its first great transformation, the moment when atoms would finally form, when light would be set free, and when the cosmos would, for the first time, become transparent. But before that moment arrived, this primordial soup had one last task: to hold its shape long enough for gravity to begin its slow, patient work. Those faint ripples in density, born in the wild first flicker of the universe, were waiting to grow. They would not be rushed. They would take millions of years to bloom into the first stars. But already, in this glowing haze, their outlines existed, invisible yet inevitable, like a map the universe itself could not help but follow. And so, the soup of particles remained, expanding, cooling, and stretching toward a future it could not yet see, but one that was already written in its structure. Because when the fog finally cleared, and the first true light escaped into the darkness, the universe would change forever. The universe had been waiting in silence, though it was not the kind of silence we know. It was a silence without darkness, a glow trapped within a dense fog, light bouncing endlessly from one particle to another, unable to escape. For hundreds of thousands of years, that was the state of everything. A bright but hidden cosmos, expanding and cooling slowly, almost patiently, as if it were holding its breath for the moment it could finally reveal itself. And then, at last, the fog began to thin. Around 380,000 years after the beginning, the universe reached a temperature where something extraordinary could finally happen. The relentless heat that had kept electrons from binding to nuclei had faded. For the first time, protons and electrons could join together and form complete atoms. It was such a simple step, but it changed everything. This moment is called recombination, though it might be more accurate to call it the first assembly of matter into something recognizable. With electrons now bound into atoms, the universe became transparent. Light, once trapped in an endless scattering haze, was suddenly free, and in that instant, the first light we could ever hope to see began its journey. That light is still travelling today. We call it the cosmic microwave background, a faint afterglow of the early universe, stretched and cooled over billions of years until it now bathes the cosmos in a nearly uniform glow. If you could somehow see it with your eyes, the entire sky would be covered in it. Not stars, not galaxies, just a soft ancient radiance left over from the moment when the universe first became clear. But it wasn't just light escaping into space. This was the first time the universe had structure that we could meaningfully describe. Atoms had formed. The fog had lifted. The rules that would govern everything from here on out were no longer buried under the weight of heat and plasma. It was as if the cosmos had taken its first deep breath and settled into the shape it would carry for the rest of time. This first light wasn't bright in the way we imagine sunlight or fire. It was soft even, and everywhere. And as it spread, it carried with it an astonishing story. Embedded within it were the faint imprints of the universe's earliest ripples, those tiny variations in density that had been stretched to enormous scales by inflation. They appeared as the slightest differences in temperature, almost invisible, but they were enough to tell us that the smooth, glowing haze of the young cosmos wasn't truly perfect, and those imperfections were everything. They were the reason matter didn't stay evenly spread forever. They were the reason gravity had something to work with, something to pull together. Without them, the universe would have been static and featureless, a vast expanse of hydrogen and helium drifting endlessly in silence. But with them, the universe had the beginnings of contrast. the first faint outlines of the cosmic web that would one day be traced by galaxies. When we look at the cosmic microwave background today, using telescopes tuned to the faint wavelengths of this ancient glow, we're not just looking at light, we're looking at the universe's first memory of itself, a snapshot from when it was still young, still simple, and yet already holding within it the pattern of everything that would follow. It's humbling to think that the photons from that era have been travelling ever since, untouched, unchanged, moving through a cosmos that would transform dramatically as they went. By the time they reach our instruments, they've been stretched by the expansion of space until their wavelengths are 1,000 times longer than they once were. What was once a fiery brilliance has cooled into a soft microwave glow, but in that dimness lies a map, a perfect, quiet record of the first light that ever was. And it's not just a relic, it's a reminder. That light is everywhere, filling every inch of space around us, a faint echo of a time when there were no stars, no planets, no observers to notice it, only a young universe glowing softly to itself. When you think about it like that, it's almost comforting. Long before there was life to ask questions, long before there was Earth to stand on, the universe was already leaving behind a message in light, one we would only learn to read billions of years later. After this great unveiling, the universe entered what might seem like a quiet age. The fog was gone, but there were still no stars. Space was vast and growing vaster. Matter drifted slowly, drawn together by gravity in an invisible dance that would take hundreds of millions of years before it finally burst into brilliance. But even in that darkness, the light of the early universe still lingered, washing over everything, a constant presence in a cosmos waiting for its next act. This was the beginning of what we call the cosmic dark ages, a long stretch of time after the first light escaped, but before the first stars were born. It sounds lonely, but it was in this apparent stillness that the seeds planted by inflation and carried by the glow of recombination began to grow. Tiny clumps of matter gathered mass. Gravity, patient and relentless, pulled gas into denser and denser regions. The universe was silent, but it was busy, quietly preparing for the moment when darkness would break for good. And it's here that the story of the first light takes on a new meaning. Because as much as this early glow marked the universe's first visible moment, it was also a promise of what was coming. In its faint patterns were the fingerprints of every future star, every galaxy, every cluster. The universe was no longer just a storm of particles and energy. It had structure now, written in light, and though it would take time for that structure to bloom into the cosmos we see today, the blueprint was already there. Even now, when scientists study that ancient glow, they find themselves looking deeper than just its faint brightness. They study its tiny variations, the way it shifts and ripples across the sky. And from those faint signals they can tell us astonishing things. The exact age of the universe, the rate of its expansion, the very nature of its geometry. In other words, the first light didn't just illuminate the universe, it illuminated the path to understanding it. But even as it did, this era was only a beginning. For all the beauty of that soft ancient glow, it was merely a backdrop, a stage waiting for the next act to begin. Because soon, in the quiet darkness that followed, gravity's slow work would pay off. Clouds of hydrogen would collapse under their own weight. Heat and pressure would rise, and from that collapse the first stars would ignite, tiny points of brilliance breaking through the darkness, carrying the universe from its first faint afterglow into a new age of light. The first light was a whisper. The stars would be the universe's first song. In the stillness that followed the universe's first light, something quiet but powerful was at work, shaping everything that would come next. Gravity, the most patient of forces, had begun to weave its invisible threads through the cosmos. It didn't roar or flash. It didn't announce itself with heat or light. It simply pulled slowly and steadily, drawing matter together step by step. until the vast, empty stretches of space began to gather into the first hints of form. For hundreds of thousands of years after that first glow escaped, the universe seemed almost uneventful. Hydrogen and helium drifted through the dark like a vast cosmic mist. There were no stars yet, no galaxies, no planets. But this wasn't emptiness. Beneath the quiet, gravity was sculpting. It was following the blueprint left behind by inflation, tracing those tiny ripples in density that had been frozen into the fabric of the early universe. In some regions, matter was ever so slightly denser than in others. The difference was almost laughably small, but gravity doesn't need much to get started. Over time, these denser spots pulled in more matter. That, in turn, made them denser still, which made their pull even stronger. It was a cycle without hurry, but with endless determination, and it marked the beginning of structure in a universe that had, until then, been little more than a glowing fog and an expanding sea of potential. This is one of the strange truths about gravity. It is the weakest of the fundamental forces, so weak that a single refrigerator magnet can lift a paperclip against the pull of an entire planet. And yet, in the scale of the cosmos, it's the one force that refuses to fade. Unlike the other forces, gravity never cancels itself out. It always adds up. Every particle of matter pulls on every other, no matter how far apart they are, and over time, that quiet accumulation wins. It was gravity, not the heat of the early universe or the brightness of the first light, that would ultimately decide what the cosmos would look like. As the universe expanded, gravity worked in the background, unnoticed but unstoppable. It took those tiny fluctuations, those barely there wrinkles left over from the earliest instant, and turned them into the scaffolding of the cosmic web. Matter flowed into those invisible valleys, gathering in filaments and knots, while vast empty regions opened up between them. Even before the first stars, the shape of the universe was already being drawn, a vast and intricate map of what would one day become galaxies and clusters. But this wasn't fast work. Gravity does not rush. For millions of years, hydrogen and helium gas simply fell inward, drawn by this gentle but relentless hand. In the darkness, the first great clouds of matter began to take shape, enormous collections of gas drifting closer and closer together. There was no light yet, only motion, only the slow gathering of material that would one day ignite. And then, in those deepening clouds, pressure began to rise. As gravity pulled gas inward, it squeezed it tighter and tighter, heating it as it collapsed. In some places, this process stalled. Clouds stabilized, still massive, but not dense enough to ignite. In others, however, gravity refused to let go. The collapse continued. Heat built, and deep in the hearts of those clouds, something new happened. Nuclear fusion, the very process that powers the stars, was born. The first stars were nothing like the sun we know today. They were giants, many times more massive, blazing hot and short-lived. They formed in isolation, scattered like lonely lanterns in a vast sea of darkness. Their light cut through the cosmic night for the first time, piercing the silence that had lasted for hundreds of millions of years. Gravity had done its work. From the faintest ripples in the early universe, it had pulled together enough matter to light the first fires of the cosmos. But even this was only the beginning of what gravity would accomplish. Those first stars were not just points of light. They were engines, burning hydrogen into helium, fusing elements in their cores, and seeding the universe with new materials when they died. Gravity brought them together, held them steady while they burned, and then, in their final moments, unleashed them in titanic explosions that scattered heavy elements into space, ready to be recycled into new stars, new planets, and one day, living things. Gravity's role didn't stop there. The same force that pulled the first clouds together also bound stars into galaxies. Over millions of years, those bright, early stars began to gather, swirling into vast collections held together by their shared pull. From those galaxies came clusters, and from those clusters came the grand cosmic web, each step an echo of the same simple rule. Matter attracts matter. And perhaps the most humbling part of all is that gravity has no end point. It doesn't finish its work and walk away. Even now, billions of years later, it's still shaping the universe. It's the reason galaxies spin in graceful spirals. It's the reason stars gather in clusters. It's the reason the moon circles Earth and Earth circles the sun. Every orbit, every structure, every connection in the universe is, in some way, gravity's quiet signature. But there's a subtle beauty in how it began. Because when we talk about the earliest universe, it's tempting to think of it as wild and chaotic, a place of unimaginable violence. And in some ways it was. But gravity's role was different. Gravity was never loud, it didn't tear or shatter, it gathered, it stitched the universe together. From the very start, it was less a force of destruction than a force of organisation, a hand that turned randomness into pattern, and emptiness into form. Even the great voids of space, those vast regions between galaxies where almost nothing exists, are part of gravity's design. They exist because gravity pulled matter away from them, flowing toward the dense filaments and knots that now hold the stars. Every bright point in the sky and every patch of darkness around it was shaped by that same invisible pull. And that pull never stops. When you look up at the night sky, the light you see is not just the story of stars. It's the story of gravity's patient work, stretching back to the first ripples in the early universe. It's a reminder that from the very beginning, even when there was no light, no galaxies, no worlds, gravity was already there, quietly writing the first lines of the cosmos we now live in. And what came next would only deepen its influence. Because as the first stars formed, gravity's reach began to weave them together into something larger. Galaxies, the grand cities of the universe, where billions of stars would gather, live, and die, each one bound by the same force that has been shaping reality since the very start. The hand that pulled the first clouds together had only just begun. The first stars had begun to burn, their light piercing the long darkness for the very first time. They were solitary beacons at first, scattered across an immense silent cosmos. But even in that apparent loneliness, something deeper was happening. Something gravity had been preparing for since the earliest moments. Hidden in the chaos, the seeds of galaxies were already taking root. When we look at the night sky today and see vast spirals and glowing clusters, it's easy to forget that galaxies were not born in their graceful forms. They began as something far less defined, quiet concentrations of matter gathered by the faint ripples imprinted on the universe during its earliest fractions of a second. These ripples, tiny fluctuations in density stretched to cosmic scales by inflation, were almost imperceptible then, but they were enough. Gravity is patient. It takes the smallest differences and amplifies them over time. In the vast haze of hydrogen and helium that filled the young universe, these slightly denser regions began to draw matter inward. The process was slow. Millions of years passed as invisible scaffolding formed in the darkness, a web of matter converging on itself. This web wasn't random. It followed the pattern laid out by those first fluctuations, growing denser where the initial blueprint had been marked, and thinning in the vast spaces between. And here's the part that makes the early universe even stranger. Much of this web was made of something we still can't see. Dark matter, mysterious, invisible, and detectable only by its gravity, was already there, outweighing normal matter by more than 5 to 1. It didn't shine, it didn't interact with light, and yet it provided the framework for everything. While ordinary matter floated in the cosmic sea of radiation, dark matter was already clustering, pulling the first threads of structure tight. Over time, these dark matter clumps became gravitational anchors. They were the unseen skeleton of the universe, and normal matter, the hydrogen and helium left over from the Big Bang, fell into their grip. Slowly, clouds of gas began to pool in these dark matter wells. There were no stars yet in these early gatherings, just vast reservoirs of raw material swirling and colliding, but the stage was set. As the gas collapsed, it began to fragment, breaking into smaller pockets. In those dense knots, gravity squeezed matter tighter, heating it until nuclear fusion could ignite. The first stars formed within these halos of dark matter, their light spilling out into the vast dark. And as more stars were born, their gravity deepened the pull, drawing in still more matter. This was how the first galaxies began, not as grand spirals or elegant ellipses, but as small, irregular swarms of stars, their shapes unsteady and chaotic. Over time, some of these primitive galaxies would collide and merge, drawn together by their mutual gravity. Each merger added to their mass, reshaping them, feeding the growth of larger, more complex systems. In the chaos of those early collisions, the first galactic giants were born. It's strange to imagine it, but if you could have stood in the young universe, though of course there was no place to stand, you wouldn't have seen the clean order we see today. You would have seen a restless, turbulent cosmos full of swirling clouds of gas, brilliant newborn stars, and galaxies that were only beginning to find their form. And even then, gravity wasn't finished. It gathered galaxies into clusters, and clusters into superclusters, all connected by vast filaments of matter. Between them, enormous voids opened up, stretches of almost perfect emptiness. This cosmic web, stretching across billions of light years, was born from the quietest beginnings, those tiny fluctuations magnified by gravity and nurtured in the invisible framework of dark matter. What's remarkable is that we can still see traces of this process today. When astronomers map the large-scale structure of the universe, they find that galaxies aren't scattered randomly. They trace out the same vast network, the same hidden web that began forming in the first billion years. The seeds planted in the early universe didn't just create galaxies, they shaped the entire layout of the cosmos, a structure so immense that it stretches beyond anything we can directly see. And yet, even as the universe was building this grand architecture, it remained in a state of restless transformation. The first galaxies were small and unruly, full of massive stars that burned fast and died young. When those stars exploded as supernovae, they hurled heavy elements, carbon, oxygen, iron, back into space, enriching the gas that would form the next generation of stars. Slowly, from one cycle of birth and death to the next, galaxies began to change. They became more complex. They formed disks and bulges, spiral arms and halos. The universe was learning how to build. But in those early days, the seeds of everything were already there. Every galaxy we see today, from the smallest dwarf to the largest cluster, can trace its lineage back to those first gravitational gatherings in the dark. And though it would take billions of years for many of them to reach their full shape, the blueprint was set almost from the very beginning. What's even more humbling is that this process hasn't stopped. Galaxies are still merging, still growing, still reshaping the web they trace. When we look out into deep space with our most powerful telescopes, we see galaxies in all stages of their lives, some just beginning, some colliding in chaotic swirls, and others, like our own Milky Way, settled into a quieter maturity but still bound by the same invisible threads of gravity that have guided them from the start. And it all began with those hidden seeds, scattered in the chaos of the early universe, waiting for gravity's patient hand to bring them together. From here, the story would only become richer. The galaxies that had taken shape would soon become the homes of stars and worlds. But before any of that could happen, the universe still had to move through its next chapter, an era that would bring both light and shadow as the great web of matter deepened and the night began to fill with brilliance. After the first galaxies began to take root, the universe entered one of its strangest and quietest chapters. We call it the Cosmic Dark Ages, though that name is almost misleading. It wasn't empty, and it wasn't silent. It was simply a time without visible light, a long and patient interval between the first glow of the cosmos and the moment when stars and galaxies would fully transform the darkness into a sky blazing with brilliance. To understand this era, imagine the universe as it was after the first light escaped, transparent, cooling, and filled with hydrogen and helium gas. The fog had lifted, but the cosmos was still almost completely dark to the human eye. There were no stars bright enough yet to push back the blackness on a grand scale. The first stars had formed, yes, but they were scattered and rare, tiny pinpricks of light lost in an ocean of shadow. For hundreds of millions of years, this was the state of the universe, a vast and quiet darkness, slowly, almost imperceptibly, shifting towards something new. This was not an age of stillness. Beneath that dark canvas, gravity was still at work, silently drawing matter into denser regions. Small proto-galaxies were forming, clumps of gas collapsing under their own pull, merging and colliding in a slow and steady march toward complexity. But these processes took time. In the grand scale of the universe, millions of years passed like deep, patient breaths. Inside those dense pockets of gas, the first stars blazed, enormous and short-lived. These stars were far larger than the ones we see today, their lifespans brief but transformative. They burned their fuel in a furious rush, living for only a few million years before dying in spectacular explosions. When they died, they scattered the first heavy elements into space: carbon, oxygen, and iron, seeding the cosmos with the ingredients that would one day form planets and life. And yet, even with these first stellar deaths and rebirths, the universe remained mostly dark. These early stars were not enough to flood the cosmos with light. Their glow was faint compared to the vastness around them. Much of the gas between galaxies remained neutral, unlit and opaque to the kind of light that could travel freely. The universe was in a liminal state, no longer the bright plasma of its first moments, but not yet the star-filled expanse we know today. This is what made the cosmic dark ages so profound. It was an era of preparation, a kind of cosmic pause where the stage was being set for what was to come. The first galaxies were assembling quietly in the shadows. Dark matter continued to shape the great web of structure, deepening the gravitational wells where gas could gather. And all the while, the universe itself was expanding, stretching the distances between these growing islands of matter, even as it provided the time and space they needed to form. During this time, something else remarkable was happening: the birth of the first black holes. Some of the most massive early stars, unable to withstand their own weight when their fuel ran out, collapsed in on themselves, forming dark, invisible points of gravity so intense that nothing could escape their pull, not even light. These black holes would become the seeds of the supermassive giants we find at the centres of galaxies today, including our own Milky Way. Even in the darkness, the universe was planting the anchors of its future. But as the Dark Ages stretched on, the balance was slowly tipping. Every generation of stars forged new elements. Every explosion enriched the gas around it, and with each new cycle, the universe crept closer to a turning point. Eventually, the stars became numerous enough, their radiation strong enough, to begin transforming their surroundings. Their light started to strip electrons from the neutral hydrogen gas between galaxies, a process known as ionization. It was the beginning of the end for the cosmic dark ages. This transformation didn't happen all at once. It was gradual, a slow ignition spreading across the universe. Small bubbles of ionized gas formed around the earliest galaxies, little pockets of clarity where light could travel freely. Over time, these bubbles grew, merged, and connected, until the darkness that had reigned for hundreds of millions of years began to fade. For the first time since its birth, the universe was becoming a place filled with light. When we look back at this era with our most powerful telescopes, we can see glimpses of this transformation. We see the faintest galaxies, barely visible specks from a time when the cosmos was just emerging from its long night. These early galaxies are young and chaotic, their stars burning hot and blue, their light piercing a universe that had been waiting in shadow for so long. And yet, even as light began to spread, darkness never truly left. It receded, but it remained between galaxies, in the vast empty stretches of space where no stars shine. The cosmic dark ages ended, but they left their mark on the structure of the universe, shaping the web of matter and the distribution of light and shadow that we still see today. It's strange to think that in those silent, dark centuries, everything that would define the universe was already underway. Galaxies were forming, black holes were awakening, stars were being born, burning out and scattering the elements for the next generation. In that darkness, the universe was quietly becoming itself. If there's a lesson in this part of the story, it's that not every transformation is loud. Some of the most profound changes happen in silence, in the spaces between what we can see. The Long Age of Darkness was exactly that. A hidden era, almost invisible to us now, but absolutely essential. Without it, there would have been no time for galaxies to grow, no stars to ignite in great numbers, no foundation for the cosmic dawn that followed. Because after this long night, light returned in earnest. The first great era of stars and galaxies was about to begin, and the universe, once quiet and dark, would burst into brilliance, filling the sky with more light than it had ever known before. And in that first true dawn of starlight, the cosmos would finally start to look a little more like the universe we see today. Out of the long silence of the cosmic dark ages, something extraordinary began to happen. In the cold, vast stretches of space, inside deep clouds of hydrogen and helium, the quiet pull of gravity reached its tipping point. Gas collapsed in on itself, heat and pressure rose, and then, for the first time in hundreds of millions of years, the universe lit its first lanterns. The first stars were unlike anything we see today. They were giants, enormous, hot and short-lived. Many were hundreds of times the mass of our sun, their cores burning with a fury we can hardly imagine. These stars didn't flicker gently into existence. They roared to life, their light slicing through the darkness that had ruled the cosmos since its beginning. One by one, scattered across the vastness, they ignited, turning a silent, shadowed universe into a place of brilliant, blazing points of light. And yet, as bright as they were, these stars lived in isolation. They were not born in mature galaxies, but in small, primitive gatherings of gas and dark matter, the first halos that gravity had stitched together in the Dark Ages. These early stars burned with an intensity that came from their sheer size. Their enormous mass crushed their cores to such extremes that nuclear fusion raced ahead, consuming their fuel in only a few million years, a brief flash on the cosmic timeline. But what they lacked in longevity, they made up for in importance. These stars were alchemists. In their cores, hydrogen fused into helium, and helium into heavier elements. When they reached the end of their lives, they exploded in violent supernovae, scattering those elements into space. Carbon, oxygen, iron. These building blocks of planets, and, eventually life itself, were born in those first titanic fires. Without them, the universe would have remained nothing but hydrogen and helium, a place without the raw materials for complexity. Imagine the sky of that time. No constellations, no galaxies as we know them, only an immense void dotted with solitary massive stars, their light pushing back the darkness in lonely, scattered bursts. These were the first beacons in a universe still learning how to shine. As more stars were born, their combined light began to transform their surroundings. Ultraviolet radiation from these stellar giants poured into the intergalactic medium, stripping electrons from atoms and reionizing the hydrogen gas that filled space. It was this process that finally ended the cosmic dark ages for good. Slowly, pockets of ionized gas spread outward from each star, from each small cluster, until they merged into great regions of clear, transparent space. This was the cosmic dawn, the moment the universe began to shift from darkness into light. It was not a single event, but a slow, unstoppable wave of illumination that spread across hundreds of millions of years. Each new star added its brilliance to the growing radiance, and as the first primitive galaxies formed, their combined glow became bright enough to reshape the universe forever. But there was more happening in those first stars than just light. Their deaths were as important as their lives. The most massive of them, unable to resist the pull of their own gravity when their fuel was spent, collapsed into black holes. These early black holes, some formed directly from the cores of those first stars, became seeds for the supermassive giants that now sit at the centres of galaxies. In their own way, these deaths were part of creation. From the violent ends of those first stars, the universe planted the anchors that would hold entire galaxies together. Meanwhile, smaller stars, those that burned less furiously, began to form alongside the giants. These stars lived longer, giving the young universe its first enduring sources of light. Around them, gas clouds were stirred and enriched by the elements left behind from earlier stellar explosions. The universe was becoming layered, each generation of stars building upon the last, each one transforming its surroundings and making the cosmos more complex. And gravity, as always, was the quiet hand guiding it all. It pulled stars together into clusters, clusters into early galaxies, and galaxies into the great structures of the cosmic web. What began as isolated sparks in the void was becoming a grand tapestry of light. If we could somehow watch this transformation unfold in real time, it would be breathtaking. In the earliest moments, you'd see only a few lonely stars shining against an endless sea of black. But then, slowly, more would appear. Pockets of light would bloom, faint and far apart at first, then growing closer and brighter, until the darkness was no longer empty but filled with a scattered glow. Over hundreds of millions of years, that scattered glow would knit itself into something greater, the first recognisable patterns of the universe we know today. And even though we can't witness it directly with our eyes, we've caught glimpses of this era through the most powerful telescopes ever built. When astronomers peer deep into the sky, they are looking back in time. They've seen the faint light of galaxies from more than 13 billion years ago. Small, irregular collections of stars, primitive and raw, but unmistakably the ancestors of the grand spirals and giant clusters that now fill the cosmos. Every time we look at them, we are seeing the universe as it was in its youth, lit for the first time by these cosmic lanterns. They are reminders that everything we see today, every galaxy and every star, grew out of those early points of brilliance that dared to shine against the vast dark. And that light, once it began, never truly stopped. It grew, it spread, it drew matter into new shapes, formed heavier elements, and laid the groundwork for planets, and eventually life. The universe was no longer simply expanding, it was evolving, its story written not just in darkness, but in the radiance of countless stars. But even as the first stars illuminated the void, something else was stirring in the shadows. The galaxies that housed them were growing, colliding and merging in a great unseen dance. And from that dance, the universe was preparing to build the grand structures that would shape everything that followed. The first stars were brilliant, but they were not built to last. Many of them were giants, burning through their fuel with a speed that made their lives fleeting. And when their short lives came to an end, they didn't fade quietly. They died in the most spectacular way imaginable. They exploded. A supernova is not just an ending, it is a transformation. In those first titanic deaths, the universe learned how to recycle. When a massive star exhausted its fuel, its core collapsed under the crushing weight of gravity. In that instant, everything changed. The core imploded, and then, in a fraction of a second, it rebounded in a titanic blast, hurling the star's outer layers into space at incredible speeds. For a brief moment, the explosion outshone entire galaxies. The light from these first supernovae cut across the darkness of the young cosmos, brighter than anything that had come before. But the brilliance was only part of the story. These explosions were the universe's first great act of creation through destruction. Inside those stars, fusion had forged the elements. Hydrogen into helium, helium into carbon, oxygen, silicon, and eventually iron. But iron was the limit. Fusion could go no further. And so, in those violent deaths, the universe unlocked something new. In the unimaginable heat and pressure of a supernova, heavier elements were born: gold, uranium, and other materials that would one day be scattered into planets, and eventually into living things. This is the quiet truth of the cosmos. Everything we are, everything we touch, was forged in the heart of a star that died long before our sun was born. Every atom of iron in your blood, every bit of calcium in your bones, every trace of gold or copper in the ground. It all began in the cores of stars that lived and died billions of years ago. Supernovae were not just spectacular events. They were the mechanism by which the universe became rich enough for complexity. After each explosion, the remnants of those first stars were cast out into space. Clouds of enriched gas spread into their surroundings, mixing with the hydrogen and helium that still dominated the universe. These materials didn't disappear. Gravity gathered them up again, folding them into new clouds of gas that would collapse to form the next generation of stars. Those stars would be slightly different, smaller, longer-lived, and surrounded by material seeded with the elements of the first generation's deaths. This cycle, birth, death, and rebirth, became the heartbeat of the universe. It was through this process of cosmic recycling that the raw, simple matter of the early universe evolved into the rich, element-filled cosmos we know today. Without those first supernovae, there would have been no planets, no oceans, no life. But those explosions did more than create the ingredients for the future. They also reshaped their surroundings in dramatic ways. When a massive star exploded, its shockwaves rippled outward, compressing nearby gas clouds. That compression could trigger the birth of new stars, setting off a chain reaction of creation. In this way, the deaths of the first stars didn't just mark an ending, they ignited the next wave of cosmic growth. And then there were the black holes. Some of the most massive stars didn't scatter their remains into space. Instead, their cores collapsed so completely that nothing could escape their pull. These first black holes became gravitational anchors, lurking silently in the centres of their stellar neighbourhoods. Over time, they would grow, feeding on gas and dust, merging with others, and eventually becoming the monstrous, supermassive black holes that now sit at the hearts of galaxies. Meanwhile, other supernovae left behind neutron stars, small, incredibly dense remnants, no larger than a city but heavier than our sun. These strange objects, spinning rapidly and beaming radiation into space, were yet another product of the universe's new ability to recycle itself. Every outcome of a star's death left an imprint on the cosmos, adding to its growing complexity. As the cycles of starbirth and death repeated, galaxies began to change. The first, chaotic clouds of stars and gas grew larger and more structured. They collided and merged, pulling in new material, feeding their black holes and forging new generations of stars. Each cycle enriched the universe a little more, filling it with the elements needed not only for new stars but for worlds. And it all came from these explosions, the universe's way of renewing itself. Supernovae were the engines of progress, scattering the ashes of dead stars into the vastness, where gravity patiently gathered them back again. Even now, billions of years later, this process has never stopped. Stars are born, live their lives, and die. And from their deaths, new stars rise in their place. It is one of the few constants in the story of the cosmos. Creation and destruction bound together in a single, endless rhythm. When we look at the universe today, we can still see the echoes of those early explosions, the glowing remnants of supernovae, vast expanding clouds of gas, dot our galaxy and others, beautiful and haunting reminders of the violent process that made everything possible. They are monuments to the way the universe builds itself, piece by piece, from the wreckage of its own stars. But those early supernovae were more than just the first fireworks of the cosmos. They were the moment when the universe began to take its first real steps toward the kind of richness and complexity that would define its later history. They lit the sky with light and heavy elements. They stirred the gas between the stars, shaping the conditions for new generations of stars and galaxies. They even laid the groundwork for the eventual formation of planets, small, solid places where matter could settle and organise itself in entirely new ways. And so, in that deep, ancient darkness, every explosion was more than just an ending. Each one was a promise of what would come next. The universe had found its way of growing, not in silence, but in a rhythm of fire and renewal. And as the explosions continued, and as galaxies collided and merged, the cosmos itself became a vast, interwoven network of these cycles. From the scattered remnants of dead stars, new stars formed, new light was born, and the universe slowly became what we see now. A place not just of energy and expansion, but of constant transformation. Yet even this was only one chapter, because as supernovae lit the young cosmos with their brilliance, another force was quietly shaping everything on a grander scale, weaving the stars into the vast structures that would define the universe for billions of years to come. In the glowing aftermath of the first stars and their brilliant deaths, as the universe filled itself with new light and new elements, there was another presence forming quietly in the background. These were not bright beacons or dazzling explosions. They were silent, hidden, and far stranger than anything that had come before. They were black holes, the shadows in the early light of the cosmos. The first black holes were born from the deaths of the universe's earliest giants. When the most massive stars burned through their fuel, their cores could no longer fight the relentless inward pull of gravity. The collapse was unstoppable. The star's heart fell inward, shrinking past the point where any known force could resist it. For a fleeting instant, the collapsing core might have been no larger than a world, then no larger than a city, and then it was gone, falling into itself, vanishing from view, leaving behind nothing but an invisible region of gravity so strong that not even light could escape. And just like that, the first black holes were born. At first they were small by cosmic standards, remnants of single stars scattered across the young universe. Yet even then their presence was profound. These invisible objects were like gravitational anchors, shaping the matter around them in quiet but decisive ways. As they drifted through the dense, gas-rich early cosmos, they began to feed. Black holes grow by consuming. Any gas, dust, or even stray stars that wandered too close would be pulled toward them, spiraling inward and vanishing across the event horizon, the point of no return. Paradoxically, this process of feeding could be anything but silent. As matter fell in, it didn't simply disappear, it heated up, swirling into disks of superheated gas that could shine brighter than entire galaxies. Around these black holes, some of the first quasars were born, beacons of light powered by darkness, outshining everything around them. Even stranger, these first black holes didn't remain small for long. Some of them, for reasons we are still working to understand, grew with astonishing speed. In only a few 100 million years, a handful of them swelled into monsters millions or even billions of times the mass of the Sun. These became the seeds of the supermassive black holes that now rest in the centres of galaxies, including our own Milky Way. How they grew so quickly remains one of the great puzzles of cosmology. Some scientists think they began as unusually large stellar remnants, black holes many times the mass of the Sun that formed directly from the collapse of the earlier stars. Others believe they might have formed from the direct collapse of enormous gas clouds, skipping the stage of becoming stars entirely. Whatever the mechanism, the result was the same: colossal engines of gravity that began to shape the very galaxies around them. In those early days, as galaxies were still forming and merging, black holes were not just passengers, they were architects. Their immense gravity influenced the motion of stars and gas, stirring the material in their host galaxies and regulating the pace at which new stars could form. When a black hole fed, it could unleash jets of energy powerful enough to blast matter outward, sculpting its surroundings in ways that reached across tens of thousands of light years. It's one of the strangest truths about the universe. The darkest objects we know, the ones that let no light escape, have played a central role in shaping the bright star-filled cosmos we see today. Without black holes, galaxies might have grown too fast or too chaotically, burning through their gas and collapsing into disarray. Instead, these hidden giants acted as regulators, balancing the growth of their host galaxies and helping to create the orderly structures that now fill the universe. And they were there from the very beginning, even as the first light of stars spread across the dark. While supernovae seeded the cosmos with elements, while galaxies gathered and merged, black holes watched silently. Their influence felt more than seen. They were shadows at the heart of creation, present from the start and destined to remain until the very end. What's even more humbling is that these early black holes may hold the key to understanding not only the past, but the future. Today, every major galaxy we've observed has a supermassive black hole at its core, a gravitational monarch sitting in quiet dominance. Our own galaxy's central black hole, Sagittarius A, is calm now, but in the distant past it may have been a quasar, blazing with the energy of matter falling into its maw. And long after the stars have burned out and the galaxies have faded, black holes may be the last great structures left standing, the final echoes of a universe that once burned with light. But in the young cosmos, these shadows were not yet the end. They were part of the beginning. They pulled matter inward, they fed and grew, and they shaped the paths of stars and galaxies alike. They were the silent counterparts to the brilliance of the first stars, the dark centres around which the early universe learned to organise itself. And as the ages passed, as galaxies formed in greater numbers and stars lit up the sky by the billions, these hidden engines of gravity never stopped working. They continued to merge, to feed, and to carve their mark into the structure of the cosmos. And in their quiet way, they made possible the next great chapter, the rise of the vast cosmic web, where galaxies became not just isolated islands of stars, but part of an interconnected, boundless structure stretching across the universe. The early universe was no longer a simple place. Light and darkness, creation and destruction, stars and black holes, all of them were locked in a single grand story, and it was only just beginning to unfold. As the universe aged past its first billion years, it was no longer only a scattered collection of stars and galaxies. Something larger and far more intricate was emerging. Invisible at first, but undeniable in its influence, gravity had been quietly sculpting the cosmos into a vast interconnected network. This was the great web of cosmic structure, a lattice of unimaginable scale that linked everything together, from the smallest dwarf galaxies to the largest clusters, spanning billions of light years across the dark. If you could step outside the universe and look back at it all at once, it would not resemble a random scattering of galaxies. It would look like a web, delicate but immense, with glowing filaments of matter stretching across the cosmic void. Along these filaments, galaxies gathered like dew on a spider's thread, clustered in knots where the strands crossed, while between them yawned immense voids, regions of almost perfect emptiness, vast enough to swallow entire superclusters without a trace. This structure didn't appear overnight. Its roots go all the way back to those tiny fluctuations in density that inflation had imprinted onto the newborn universe. At first, those variations were almost imperceptible, but gravity has a way of magnifying even the faintest differences. Over hundreds of millions of years, matter flowed toward the slightly denser regions, pulled along invisible channels shaped by dark matter. Dark matter was the hidden architect here. Though we still cannot see it, its gravity outweighs that of normal matter by more than 5 to 1. It was dark matter that formed the skeleton of the cosmic web, gathering into vast invisible filaments that guided the flow of gas and stars. The galaxies we see today are simply the luminous traces of that invisible framework, strung like beads along threads of something we cannot touch, but that defines the very shape of the universe. In those early ages, as the first galaxies ignited, they did so within these dark matter filaments, drawn together by the quiet but relentless pull of gravity. Small galaxies merged into larger ones. Clusters formed where filaments intersected, and slowly the web became clearer, more defined. It was an era of both construction and collision, as the universe learned to assemble itself on scales so vast that they defy the imagination. And in the spaces between, those enormous cosmic voids, gravity pulled matter away, leaving behind great expanses of almost nothing at all. These voids are not empty in the strictest sense, but compared to the luminous filaments, they are silent deserts. They are as much a part of the structure as the galaxies themselves, vast pockets of stillness that make the bright threads of the web stand out all the more. Even today, billions of years later, the cosmic web is still there, stretching across the sky in every direction. We cannot see it directly with our eyes, but with powerful telescopes and careful measurements, we can map it. Astronomers trace the distribution of galaxies, chart the way light bends around invisible masses through gravitational lensing, and follow the faint glow of intergalactic gas. Piece by piece, these observations reveal the same grand picture, an enormous network, an ancient blueprint etched into the universe itself. And within this structure, everything we know has its place. Our galaxy, the Milky Way, is just one of billions, strung along a filament like a single jewel in a chain that stretches beyond our view. We live in the outskirts of a galactic cluster, which is itself bound to even larger structures. No galaxy stands alone. Every one of them is a part of this vast interconnected whole, held together by the same quiet hand that has been shaping the universe since its first moments. But this web is not static. It grows. Galaxies continue to merge, clusters collide, and filaments draw in new matter from the surrounding voids. Over time, the web becomes sharper and more intricate, its threads tightening as gravity deepens its grip. And yet, even as it grows more defined, it also drifts apart. The expansion of the universe, driven by the strange force we call dark energy, is stretching space itself, pulling the great filaments farther from one another even as they grow denser within their own threads. This dual motion, contraction within and expansion without, is one of the most extraordinary aspects of the cosmos. On small scales, gravity rules. It binds stars into galaxies, galaxies into clusters, and clusters into superclusters. But on the larger scales, dark energy dominates, driving everything apart, ensuring that the great web stretches ever wider, its luminous strands drifting farther into the cosmic distance. It is a delicate balance, and it has been in place for nearly the entire history of the universe. The great web we see today is the product of this tension, this interplay between gravity's desire to pull together and the universe's tendency to expand outward. Neither force wins completely. Instead, they create the structure that we now call home, a universe vast enough to be endless from our perspective, but patterned with a coherence that began in the faintest ripples of its earliest moments. When we study the cosmic web, we are not just mapping galaxies, we are looking at the fossil record of the universe's growth, a record written not in stone but in space itself. Every filament, every cluster, every yawning void tells the same story, that from a nearly featureless beginning, gravity sculpted a masterpiece of structure, and it is still at work, still refining the edges, still shaping the future of the cosmos. And in that structure, the story of everything else unfolds. Within the filaments of the web, galaxies spin and form stars. Around those stars, planets take shape. And on one tiny world, in a small corner of a modest galaxy, beings have appeared who can look out at the web that gave them their place and ask how it all began. But even as we map this grand design, it's worth remembering that the cosmic web is not the end of the story. It is only the framework. Inside its filaments, the true details of the universe would continue to unfold. Stars would form in waves, galaxies would collide and transform, black holes would grow ever larger in the shadows of their brilliant hosts. The universe was no longer a blank canvas. It had structure now, a scaffold vast enough to hold everything that would come, and from here, the next great act was ready to begin. The refinement of galaxies themselves, the slow shaping of the universe into the familiar patterns we see today when we look up at the night sky. Inside the vast filaments of the cosmic web, where gravity had drawn matter into long luminous threads, something extraordinary was happening. The universe was no longer just a network of gas and dark matter, scattered with isolated bursts of light from the first stars. It was becoming organised. The earliest galaxies, rough and irregular at first, were beginning to take shape, finding their place within the grand architecture that had been building since the very beginning. The first galaxies did not look like the graceful spirals or sprawling ellipticals we see today. They were small, chaotic and turbulent, gatherings of stars clumped together in ways that seemed almost accidental. Many of them formed from the merging of smaller structures, pulled together by the irresistible tug of gravity. These early galaxies were the universe's first great experiments in order, messy but determined, as if the cosmos itself was still learning how to build. At their hearts, enormous clouds of gas collided and condensed, feeding furious bursts of star formation. Some galaxies may have created thousands of stars in a single year, their brilliance lighting up their surroundings against the backdrop of darkness that still stretched between the filaments. Black holes, born from the deaths of the first massive stars, were growing as well, feeding on the dense material around them and anchoring the centres of these young galaxies. In these early epochs, galactic collisions were common, space was vast, but galaxies were closer together than they are today, and gravity had a way of bringing them into each other's paths. When they collided, it was not the catastrophic impact we might imagine. Stars within galaxies are so far apart that most never came close enough to touch. Instead, these mergers reshape the galaxies themselves, blending their gas, stirring their stars, and sometimes triggering explosive bursts of star formation as new material was forced inward. Over billions of years, these cosmic collisions built larger and larger galaxies. Small, irregular clumps gave way to grander, more organised structures. Spirals began to unfurl their arms, vast rivers of stars and dust rotating around dense, glowing centres. Elliptical galaxies formed from major mergers, their stars thrown into smooth, rounded orbits, glowing like great, golden cities in the deep night. And through it all, gravity remained the quiet architect. It held these immense structures together, binding billions of stars into single unified systems. Dark matter, unseen but indispensable, formed invisible halos around each galaxy, extending far beyond the glow of their starlight. Without this dark skeleton, galaxies could not have held themselves together. Their spinning stars would have flown apart into the void. As galaxies matured, their character began to change. Star formation slowed in some, while others continued to burn bright with new generations of stars. In the crowded centres of galaxy clusters, collisions and mergers were more frequent, producing massive elliptical galaxies that now dominate those regions. In quieter stretches of space, far from the busiest intersections of the cosmic web, spiral galaxies thrived, their elegant arms tracing the pathways of stars born from long-settled gas. Among these spirals, one galaxy would eventually form that would come to hold a special place in this story. It began like countless others, as a small, irregular collection of stars and gas, shaped by gravity, built by mergers, and enriched by the deaths of ancient stars. Over billions of years it would grow, its spiral arms unfurling, its stars multiplying, until it became the Milky Way. A single galaxy among billions, but destined to be the one that would cradle a small blue world where beings would one day look up and wonder how it all began. But in those early days, galaxies were still young. Their shapes were only just emerging. Some spun themselves into disks and developed the first faint arms. Others swirled and merged, becoming featureless ellipses, their star-forming gas stripped away by the violence of their collisions. And some remained small and irregular, dwarfs clinging to the edges of larger galaxies, satellites orbiting the giants that would one day dominate the night sky. And while these galaxies formed and grew, the universe was changing around them. Expansion continued to stretch space, creating ever larger distances between the great filaments of the cosmic web. Within the filaments themselves, however, gravity was in full command, knitting galaxies into clusters and binding those clusters into vast superclusters. Even now, billions of years later, we can trace this history in the galaxies we see. The oldest stars in their halos are fossils of a younger, rougher cosmos, remnants of those chaotic early times when galaxies were smaller and the universe was still forging itself. Every spiral arm, every elliptical glow, every faint dwarf galaxy on the fringes carries within it the memory of that era, the record of how structure grew from chaos. But the story of galaxies isn't just a story of stars, it's also a story of what happens between the stars, the gas and dust that linger, waiting to be drawn into new suns, the black holes that anchor the centres of galaxies, sometimes quiet, sometimes blazing, as quasars bright enough to drown out their host, and the invisible dark matter that keeps everything bound together in ways we still don't fully understand. This was the universe learning its craft. It had moved beyond the simple beginnings of hydrogen and helium, beyond the lonely glow of its first stars, into an age of true architecture. And as galaxies took shape, the stage was finally set for the cosmos to build not only stars and clusters, but eventually the kind of worlds that could look back on it all in wonder. Yet even in this moment of creation, the story was far from over. Galaxies would continue to grow. They would collide, merge, and change. They would become the sprawling, magnificent structures we see today, each one carrying with it a history written in light and shadow. And within them, the stars would keep burning, endlessly repeating the cycle of birth and death that had begun so long ago. A cycle that would not only light the cosmos, but prepare it, piece by piece, for the possibility of something more. Because after the great age of galactic formation, the universe would face its next transformation, a quiet but profound shift in how it moved and changed. Expansion would no longer just continue, it would begin to accelerate, driven by a mysterious force we still cannot see. And with that, the universe would enter the next stage of its story, the slow drift of time and space, and the deepening mystery of why the cosmos is growing faster than it should. As galaxies settled into their shapes and the great web of structure stretched across the cosmos, the universe entered a slower rhythm. The violent births and collisions of the earliest eras had not ended, but they had softened. The cosmos was no longer only a place of chaos and sudden transformation. It had become a place of steady motion, of a quiet, almost imperceptible drift through time and expansion. By now, the universe was billions of years old. Galaxies had taken root along the threads of dark matter. Stars burned in their countless billions, and black holes watched silently from the centres of their host galaxies. The fierce, fiery beginnings of everything had given way to a grand and steady unfolding. The universe was not static, far from it. but its changes had stretched into scales so vast that to an observer within it, it might almost have seemed calm. At the heart of this quiet drift was expansion. Since the moment of its birth, the universe had been stretching, carrying galaxies farther apart from one another. At first, that expansion had been almost unthinkably fast, driven by inflation. Later, it slowed, as gravity tried to pull matter back together. But even gravity, with all its patience and persistence, could not halt the expansion. The universe simply kept growing, and the fabric of space itself continued to stretch between the great islands of matter. For a time, many believed this expansion might eventually slow down and even reverse. Perhaps gravity would one day overcome it, pulling everything back together in a big crunch, collapsing the universe into a single dense point again. But as our instruments became sharper and our measurements more precise, we discovered something far stranger. Instead of slowing, the expansion was speeding up. This acceleration was the work of something we still do not fully understand. Dark energy. It is everywhere, woven into the fabric of space itself, a force that pushes rather than pulls. It does not gather or clump like matter or dark matter. It simply drives the expansion, making the universe larger and emptier with every passing moment. In this quiet drift of time and expansion, a strange duality emerged. On small scales, gravity still ruled. Stars formed in galaxies. Planets spun around their suns. Black holes shaped the fates of their neighbourhoods. But on the larger scales, where galaxies themselves were the pieces in play, it was dark energy that held sway. The great cosmic web was still there, but its filaments were stretching, its vast threads slowly pulling away from one another, and the empty voids between them were widening. Yet for all this vast motion inside those galaxies, time unfolded in a different way. Stars aged. Some of them swelled into red giants, shedding their outer layers before fading into white dwarfs. Others, the most massive, exploded in brilliant supernovae, leaving behind black holes or neutron stars. New stars were born from the gas left behind, smaller and longer lived than the giants of the early universe. The great cosmic furnace that had once burned so hot and fast was cooling, settling into a quieter, steadier glow. And through it all, the expansion of space carried on, indifferent and unstoppable. Every second that passed stretched the distances between galaxies a little more. To us, the nearest stars in our galaxy remained fixed in familiar constellations, but beyond our galactic borders, entire clusters are slipping away, carried outward by the expanding fabric of space. One day, far in the future, their light will no longer reach us. They will drift beyond a horizon defined not by our eyes or our instruments, but by the speed of space itself. Even so, this quiet drift is not empty. It is, in its way, the most remarkable part of the universe's story. After the great convulsions of its birth, after the first stars and the wild collisions that built the earliest galaxies, the cosmos has settled into an era of balance, one where matter and energy have found their places, and the grand structures of the universe simply move outward together in silence. But this silence is deceptive. In the depths of galaxies, change never stops. Gravity continues to pull gas into new stars. Black holes keep feeding in their slow, patient way. Stellar winds and supernova stir the interstellar medium, mixing it like a cosmic ocean. On scales too vast to notice in a single lifetime, galaxies collide and merge, sometimes in events so slow that the entire process takes billions of years. Even our own Milky Way is drifting toward its eventual meeting with the Andromeda Galaxy, a collision that will reshape both, but unfold too slowly for any single observer to see. This is the rhythm of the universe now, slow, grand, and unending. The violence of the past is still there, but it is stretched thin over time, transformed into something almost serene. The cosmos is still expanding, still cooling, still evolving, but no longer with the fierce urgency of its first moments. Now, its changes are the quiet kind, the sort that only become clear when you look back across billions of years. And this quiet drift holds another truth. It is in this era, in this steady expansion, that complexity has the time to bloom. Stars live long enough for planets to form around them. Galaxies remain stable enough for new generations of stars to rise. Heavy elements forged in ancient supernovae collect into worlds, and on at least one of those worlds, life begins to wonder about its place in all of this. The universe did not need to remain in this balanced state forever. It could have been a place of endless chaos, or a place that collapsed back into itself before anything had time to emerge. Instead, it became this: a vast expanding stage where for billions of years, matter and energy have been allowed to organise themselves into the intricate, improbable structures we see today. And while this age of quiet expansion will not last forever, for now it is the era in which we live. Galaxies drift, stars shine, space stretches, time moves forward, and the universe, with its vastness and its silence, carries on, indifferent to our brief moment within it, and yet holding the very conditions that made us possible. From here, the story of the cosmos turns inward. The great web has been spun, galaxies have taken their forms, and now, within this steady expansion, the universe begins to whisper secrets from its earliest moments. Secrets carried by the faint light that has travelled to us across billions of years. Even as galaxies grew, stars burned, and the great web of cosmic structure spread across unimaginable distances, the universe never stopped carrying with it the memory of where it came from. That memory is not written in stars or in the movements of galaxies. It is written in light, faint, ancient, and all around us, a silent reminder of the moment the cosmos first became transparent. These are the cosmic background echoes, the whispers from the very beginning. When the universe was young, just 380,000 years old, it was still a blinding plasma of particles and light. Photons could not travel freely. They were trapped, endlessly scattering off electrons in every direction, bouncing from one collision to another. Space was not dark. It was glowing, but no light could escape. And then, as the universe cooled, electrons bound themselves to protons, forming the first atoms. In that instant, the fog lifted. Light, for the first time, was free to move unimpeded through space. That light has never stopped moving. It has been travelling ever since, stretching and fading as the universe expands, its wavelengths elongated until it no longer shines in the visible part of the spectrum. Today, it has cooled to a faint, almost invisible glow, known as the cosmic microwave background. And yet, this dim radiation is everywhere. No matter where you look in the sky, in every direction, those photons from nearly 14 billion years ago are still arriving, still carrying with them a picture of the universe as it once was. If you could see it with your eyes, the entire sky would be filled with this ancient glow, not in points of light like the stars we know, but as a smooth, all-encompassing wash of energy. It is not a backdrop added later. It is the original canvas on which the universe painted everything else. What makes this light so extraordinary is not just its age. It is the story it tells. When we study the cosmic microwave background with precise instruments, we see that it is not perfectly uniform. It has tiny variations, minute differences in temperature, only a few millionths of a degree. And yet, those tiny differences are the fingerprints of everything. They are the frozen traces of the quantum ripples left over from inflation, stretched across the cosmos, magnified by gravity, and etched into the glow of the early universe. These faint fluctuations are the seeds of every galaxy, every cluster, every star. Without them, the universe would have been perfectly smooth, and in perfect smoothness nothing could have formed. Gravity needs those imperfections. It needs something to pull against. And so, within the quiet map of the cosmic background, We see the blueprint of all structure, the silent beginning of everything that would one day shine in the night sky. When scientists mapped this ancient radiation in detail, they uncovered an astonishing truth. It confirmed our deepest theories about the universe's birth. Inflation, the rapid expansion that blew the cosmos up from something unimaginably small to something vast in less than a heartbeat, left behind a distinct pattern in this light, a faint but undeniable signature that we can still detect. In that pattern, the history of the universe is written as clearly as if it had been recorded on the walls of time itself. And this light carries more than just structure. It also tells us about the composition of the cosmos. By measuring the exact properties of the cosmic microwave background, we can see how much ordinary matter, and dark energy the universe contains. From this faint ancient glow, we can calculate its age, its shape, and even its ultimate fate. It is, in every sense, the universe speaking for itself, its earliest memory preserved in a form we can still read billions of years later. There is something almost haunting about it. Every particle of this radiation has been travelling since long before there were stars, long before there were galaxies, long before there was even a single world for it to fall upon. It has passed through every era of the cosmos, unchanged, carrying with it a story older than time as we experience it. When we detect it with our instruments, we are catching whispers from a moment so distant that it lies beyond imagination. And yet, for all its distance, it is everywhere. It hums softly between the stars. It fills the empty space between galaxies. It moves through you and everything you've ever known. A constant presence that asks nothing and announces nothing, simply existing as a quiet echo of the moment when light first escaped into the dark. Even the way we first discovered it feels almost accidental. In 1965, two scientists, Arno Penzias and Robert Wilson, were testing a radio antenna when they detected a faint, persistent noise that they could not eliminate. It came from every direction, at every time of day with no variation. It was not from Earth, it was not from the galaxy, it was from everywhere. They had stumbled upon the cosmic microwave background, the very afterglow of creation, humming softly across the sky. Today, our instruments have grown far more sophisticated. We can map the cosmic microwave background with exquisite precision, tracing its subtle variations across the heavens. Each new map is like peeling back the layers of the universe's history, revealing in greater and greater detail how the cosmos transitioned from a hot, uniform plasma into the structured, star-filled expanse we live in now. And yet, no matter how precise our measurements become, there is still something deeply humbling about this light. It reminds us that the universe carries its past with it. The galaxies and stars we see are only the latest chapters, but in the faint glow that surrounds us, we are looking at the first page, the place where it all began. When you imagine it this way, the cosmic microwave background becomes more than a scientific curiosity. It becomes a kind of quiet music, a note sustained across billions of years, a single, continuous thread connecting us to the first breath of the cosmos. We are not separate from it. We live within it, moving through the same ancient light that has been travelling since the dawn. And yet, even as we listen to this whisper from the beginning, it points us toward questions we cannot yet answer. What happened before this light was released? What lies beyond the horizon it defines? Is it the true beginning, or only the first visible trace of something even older, hidden behind a veil our instruments cannot pierce? The cosmic background does not answer those questions. It only gives us a place to start. A reminder that no matter how far we reach, no matter how much we learn, the universe still holds its deepest secrets in silence. But silence is not emptiness. It is a space that invites us to keep listening. The cosmic background is the earliest light we can see, a faint glow that carries us back to a universe only a few 100,000 years old. But beyond that glow, the view fades to darkness, not because there was nothing, but because light itself could not yet escape. It is there, beyond that horizon of visibility, where the most unsettling question waits, quiet but unshakable. Was there ever truly nothing? We speak of the Big Bang as if it were the beginning, but even the word beginning feels like a placeholder. We imagine a moment of absolute birth, when the universe came from nothing into something, but the closer we look, the harder that idea is to define. What does nothing really mean? If there was no space, no time, no matter, no energy, if there was not even a stage on which an event could happen, can we even call it nothing? Or is it simply a limit of our language, a word we use for a place our minds cannot reach? For centuries, thinkers argued about this very question. The ancient philosophers debated whether the cosmos had always existed, or if it was born from a void. Modern science replaced those old arguments with new mathematics and new tools, but it has not banished the mystery. If anything, the more we learn, the more we are forced to confront it. When we trace the universe back in time using the laws of physics, we eventually reach a wall, a point called the Planck time, a fraction of a second after the Big Bang so small it almost defies meaning. Beyond that point, our equations break down. Space and time themselves seem to dissolve into quantum foam, a restless sea of uncertainty where the familiar rules stop working. This is where the question of before takes root. Did the universe simply spring out of that quantum foam, the way a fluctuation can briefly appear in empty space before vanishing again? Some physicists think so. They propose that our universe is what happens when quantum possibility takes on a lasting form, that the nothing we imagine is not really nothing at all, but a state of raw potential, always there, always seething, until one fluctuation grew large enough to ignite everything we know. But there are other possibilities, and each is stranger than the last. Some theories suggest that our universe was born from another. Perhaps space and time have no single beginning, only an endless cycle. Universes expand, contract, collapse, and give birth to new universes in an infinite loop. In that case, what we call the Big Bang was not the first bang, but only the most recent echo in a sequence that has no starting point. Then there is the multiverse, the idea that our universe is just one bubble in a vast cosmic sea, each bubble its own separate reality, each with its own laws of physics. In this view, nothing is a kind of background, a quantum field from which universes are constantly budding off, each one as real and complete as ours, each one vanishingly out of reach. And yet, there is also a simpler and more unsettling possibility. Maybe there was no before at all. Maybe time itself began with the universe. In this view, asking what came before the Big Bang is like asking what lies north of the North Pole. The question collapses in on itself because it assumes a framework, time, that did not yet exist. If this is true, then the universe didn't come from nothing. It simply is. It has no before, only a beginning that is not an event in time but the origin of time itself. Each of these ideas is a doorway. None of them give us a final answer, and perhaps that's why this question lingers even after every attempt to explain it. It forces us to stand at the edge of what we can know and peer into a place where knowing itself starts to unravel. When we look out at the night sky, we see the light of stars and galaxies, the afterglow of the Big Bang, the great web of matter spun across billions of years. All of it is part of a story that unfolds within time, but if there was ever a before, it lies outside that story, in a place our minds can touch only through speculation and imagination. And maybe that is the point. Maybe this question, the question of before, is not one we answer in the usual sense. It is a reminder of how vast the mystery still is, how far the universe stretches beyond the edges of our understanding. It reminds us that everything we see, from the smallest atom to the largest galaxy, is only one chapter in a story that might reach farther than we can possibly follow. Yet even without a final answer, we've learned something remarkable from this question. we've learned that nothing in the way we usually imagine it is an illusion. The vacuum of space is not empty, it is alive with fluctuations. The moment before time may not be before at all, but a kind of primordial state where the difference between nothing and something has no meaning. And in that strange frontier, the universe found a way to begin. When we look back at the cosmic background, the oldest light in existence, we are not just looking at the start of everything. We are looking at the edge of the knowable, the point where our universe emerges from a silence so complete that even the word silence is too loud. Beyond that, there is no image, no map, only the question: was there ever truly nothing? And if there wasn't, if there was always something, even if that something was only raw possibility, then maybe the universe was never born from emptiness at all. Maybe it has always been in motion, always unfolding, even if what came before us is forever hidden from view. We may never know, but maybe knowing isn't the point. Maybe the purpose of this question is not to be solved, but to keep us listening, to keep us looking deeper, to remind us that even in a universe as vast as this, there will always be horizons just out of reach. If we follow the question of the universe's origin past the edge of what we can see, past even the faint glow of the cosmic background, we are left standing in a place where the rules we know begin to dissolve. It is here, in the strange world of the very small, that the universe may have found its beginnings. This is a realm where certainty gives way to probability, where space and time are not fixed but fluctuate, and where the first spark of existence may have emerged not from something solid or predictable, but from a restless quantum sea of possibilities. Quantum mechanics, the science of the very small, tells us that the vacuum of space is not truly empty. Even in what we think of as nothing, particles flicker in and out of existence. They are called virtual particles, and though they vanish as quickly as they appear, their existence is real enough to leave measurable effects. This restless churning of energy is sometimes called quantum foam, and in the earliest fraction of a second before the universe had any structure, it may have been the stage on which reality itself appeared. Some theories propose that our universe began as one of these fluctuations, a brief, spontaneous event in a sea of possibilities. Normally such fluctuations vanish almost instantly, but if, for reasons we do not fully understand, one of them grew instead of fading, it could have triggered inflation, ballooning into the vast expanding universe we inhabit today. In this view, there was no sharp boundary between nothing and something, only a transition from quantum uncertainty into cosmic reality. But quantum beginnings open the door to even stranger possibilities. If quantum fluctuations can give birth to one universe, why not many? Some physicists suggest that inflation may not have been a one-time event. It could still be happening endlessly, in regions far beyond what we can see. In this scenario, new universes bubble off from a larger quantum background, each one with its own version of space, time, and physical laws. Our universe, then, would be just one of countless others, an island of order in an infinite sea of quantum creation. This idea is often called the multiverse. It is vast, unsettling, and impossible to confirm with any experiment we can perform today. And yet, in some ways, it is a natural consequence of quantum theory and inflation. If true, it would mean there was never an absolute beginning, only an ongoing process of creation, with universes sprouting endlessly, each one following its own path. In such a reality, our universe is neither inevitable nor unique. It is simply one possibility among infinite others, a single thread in a tapestry too large for any observer to ever see in full. Even within our own universe, the quantum world has left its fingerprints everywhere. The tiny fluctuations that inflation stretched into cosmic scales, those faint ripples written into the cosmic microwave background, were quantum in origin. Every galaxy, every star, every world can trace its ancestry back to those microscopic tremors of uncertainty. Without quantum mechanics, there would have been no pattern for gravity to follow, no seeds for structure to grow, no universe for us to wonder about at all. And yet, for all its power, the quantum realm defies our intuition. It tells us that particles can exist in many states at once, that events are governed not by certainty but by probability, and that the very act of observing something can change its outcome. If this is what reality is made of at its deepest level, then the birth of the universe may not have been a single, definite event. It may have been a quantum branching, one path taken among countless others that might have been. Some scientists even speculate that time itself may have been born out of this quantum haze. Before the universe began to expand, before matter and energy crystallized into the forms we know, time may not have flowed the way we experience it. It may have been a kind of potential waiting to emerge once the universe settled into its expanding state. In that sense, asking what happened before the Big Bang might be meaningless, not because there was nothing, but because before was a concept that had no place in the earliest quantum state. And yet, even if these possibilities remain out of reach, they give us a way to think about the universe that is both humbling and strangely beautiful. It suggests that the cosmos is not a single, unchanging object, but a living process, one born from the most fundamental rules of nature, rules that operate in ways so far removed from our daily experience that they border on the incomprehensible. When we look at the night sky, we see the result of this quantum beginning written on the grandest possible scale. Every galaxy, every star, every atom owes its existence to the same underlying fabric of uncertainty. What began as fleeting quantum ripples became the scaffolding of the universe, stretched across billions of light years. In this way, the smallest scales of reality gave rise to the largest. Perhaps the most staggering implication of these quantum beginnings is that they may never truly end. If inflation can spawn new universes, if quantum fluctuations can generate reality again and again, then creation itself may be an ongoing process. Somewhere, beyond any horizon we can ever see, new universes may be forming even now, each one carrying its own version of space and time, its own rules, its own story. And yet, here we are, in this one, a universe born from quantum possibility, with laws finely tuned enough to allow stars to shine, planets to form, and life to wonder where it all came from. Out of the quantum fog, this is the path that unfolded. This is the universe that happened. But even if we never see beyond our own cosmic horizon, even if we never know for certain what lies in the quantum dark, we are left with a truth that is both simple and profound. The universe itself is proof that reality is stranger and richer than our instincts can comprehend. It is a reminder that everything we see was once only a ripple in the deep, silent sea of possibility. And from that sea, our story began. If there is one idea that stretches the imagination to its absolute limits, it is the possibility that our universe might not be alone. For centuries, we spoke of the universe as if it were everything, one single, infinite expanse containing all that ever was or ever will be. But as our understanding of physics has deepened, a new and unsettling question has emerged. What if our universe is only one among many? This is the concept of the multiverse, and though it may sound like speculation pulled from the edges of science fiction, it is rooted in serious attempts to explain what we see in the cosmos. It begins with a puzzle. Why does our universe have the laws of physics it does? Why is it filled with just the right amount of matter to form galaxies and stars? Why do the fundamental forces seem perfectly balanced in a way that allows complexity, planets, and even life itself to exist? If there were only one universe, these conditions might seem like an extraordinary coincidence. But if there are many universes, perhaps infinitely many, then our existence might be less a miracle and more an inevitability. In a vast multiverse, with every possible variation of physics realised somewhere, we simply find ourselves in one of the rare universes where the conditions are right for beings like us to ask these questions. One of the strongest scientific footholds for this idea comes from inflation. In its original form, inflation described a brief but staggering expansion of space in the first fraction of a second after the Big Bang, an expansion that smoothed out the universe and left it looking the way it does today. But in some versions of this theory, inflation never truly ends. It keeps going in distant regions of space, creating bubble after bubble of new universes, each cut off from the others by distances so great they can never interact. We live inside one such bubble. Outside it, there could be countless others, each with its own version of reality. Some might be similar to ours, with galaxies and stars and familiar physics. Others might be utterly alien, with laws so different that no matter, no light and no structure could ever form. And there might be universes where conditions are almost right, close enough to resemble ours, but just far enough off that nothing we would recognise could ever emerge. In this picture, the multiverse is not a single place we could travel through. It is a boundless sea of isolated realities, each one sealed off from the rest, expanding forever in its own direction. We will never see them. We will never visit them. And yet, if this theory is correct, they are as real as our own sky and our own stars. There are other hints too from the strange world of quantum mechanics. In quantum theory, particles can exist in many states at once until they are observed, at which point they seem to choose one reality. Some interpretations, like the many worlds hypothesis, suggest that nothing is ever truly chosen. Instead, every possible outcome happens, each in its own branching universe. In this view, every moment is a splitting point, where reality divides, and every possibility is realised somewhere. If true, the multiverse is not just a collection of universes born from inflation. It is an ever-branching tree of quantum histories, an inconceivable number of realities unfolding in parallel, each one as real as this one, but forever inaccessible to us. And then there are the even stranger proposals from string theory and higher dimensions, which suggest that our universe may be just one brain, floating in a higher dimensional space. In this model, other universes could exist beside ours like pages in a book, separated by dimensions we cannot perceive. Occasionally these brains might even collide, and such a collision could look, from within, very much like a Big Bang. No matter which version you consider, the idea of the multiverse forces us to confront something almost too vast to comprehend. It tells us that what we see, the stars, the galaxies, the entire observable cosmos, is not the whole of existence. It may be only one small patch in an incomprehensibly larger reality. But even if we can never see these other universes, the multiverse might still leave traces in our own. Some scientists have searched for subtle imprints, slight anomalies in the cosmic microwave background, for instance, that could be the faint scars of collisions between our universe and another. So far, no clear evidence has been found, and yet the search continues, because even the faintest sign would change everything about how we see our place in reality. If the multiverse is real, then the question, why this universe, might no longer need an answer. We live here because we could not live anywhere else. Every other version of physics exists somewhere, but this is the one that allows galaxies, stars and minds to form. In a strange way, the multiverse makes the vastness of existence both more overwhelming and strangely personal. We are here because, in one corner of an infinite sea, conditions lined up just so. And yet, there is another possibility. The multiverse could be real, and we could still be unique. Our universe, even if it is only one among many, might be the only one where life ever arose, or where consciousness ever asked its first question. In an infinity of worlds, ours might still be the only one where something looks back and wonders. Whether or not we will ever know the truth is uncertain. The multiverse may remain forever beyond the reach of observation, or perhaps someday New theories or new evidence will give us a clearer glimpse of the greater reality we now only imagine. But even without proof, the idea itself does something profound. It stretches us. It reminds us that our universe, vast as it is, might not be the final word on existence. There may be other skies, other stars, other beginnings beyond our own, each carrying its own story. And perhaps that is what makes the multiverse so powerful, not just as a scientific possibility, but as a reminder of how deep the mystery really goes. The universe we see is already more than enough to fill a lifetime of wonder. But if it is only one of many, then the true scale of existence may be something even our most daring imaginations can barely begin to touch. And yet, for all the speculation, we remain here, in this universe, under this sky, bound to the stars and galaxies we can see. This is our bubble in the sea of possibility. This is the one reality we can know, and maybe, just maybe, it is exactly the one we were meant to call home. When we look back at the beginning, tracing the universe all the way to its first moments, we're not just learning about where everything came from. We're also catching glimpses of where it might all be going. The past and the future of the cosmos are not separate. They are bound together by the same laws, the same expansion, the same quiet flow of time that has carried everything from the Big Bang to this very moment. The story begins with motion. From its earliest instant, the universe has been expanding. At first, that expansion was furious, an explosion of space itself during inflation. Later, it slowed, shaped by the pull of gravity, as matter gathered into stars, galaxies, and the great cosmic web. For a long time, it was believed that this expansion might one day stop, and perhaps even reverse, as gravity pulled everything back together into a final collapse, a big crunch that would erase everything in a single catastrophic end. But as our measurements grew sharper, a different picture emerged. Instead of slowing down, the expansion was speeding up. Some unknown force, what we now call dark energy, was pushing the universe apart faster and faster. This single discovery reshaped everything we thought we knew about the future. If this acceleration continues, then the cosmos we see today is only temporary. Over billions of years, galaxies will drift farther and farther apart. The sky will grow emptier as the most distant galaxies slip beyond the reach of our sight. The cosmic web will thin, not because the filaments themselves vanish, but because space stretches them until even light cannot cross the widening gaps. In that far future, each galaxy, or cluster of galaxies bound tightly by gravity, will become an island in an endless, expanding ocean of space. Our own Milky Way, long since merged with its neighbouring galaxies, may float alone in a darkening sky, cut off from the rest of the universe by distances no light can ever bridge. But this is only one possibility. The future of the cosmos depends on the true nature of dark energy, and though we have given it a name, we do not yet understand it. If it remains constant, expansion will continue forever. If it grows stronger, the acceleration could become catastrophic. Space itself might stretch so violently that galaxies, stars, planets, even atoms, would be torn apart in what some call the Big Rip, an end where even the smallest pieces of reality are unmade. Yet there is another scenario, one far quieter but no less final. Over unimaginable spans of time, the stars will burn out. The great engines of fusion that light the galaxies will exhaust their fuel one by one. New stars will still form for a while, but even that will slow and then stop as the raw gas needed to make them is used up. The night sky, once full of light, will begin to fade. In this heat death of the universe, energy will spread thin, stars will die, and matter itself will drift toward a state of almost perfect uniformity. Black holes will remain, swallowing whatever comes too close, but even they will not last forever. Over inconceivably long ages, they too will evaporate, fading into nothing through the slow release of Hawking radiation. And then, what is left? A universe, cold, dark, and nearly empty. a vast expanse without stars, without galaxies, without light. The story that began in a blinding flash of creation might end not with an explosion, but with silence. Yet there are other possibilities as well. Some theories suggest that the universe may not expand forever. Dark energy, mysterious as it is, might change. It could weaken, allowing gravity to reassert itself and draw everything back inward. If that happens, the cosmos could collapse into a final, crushing singularity, a mirror image of its birth, and from that collapse, perhaps another beginning, perhaps another Big Bang, a cycle of universes, each one giving birth to the next. And then there is the possibility, speculative but profound, that what we see as an ending is only a transformation. If the multiverse exists, our universe's fate might simply be one event among countless others, a single story in an endless library. Our universe might grow cold and dark, while somewhere else, another begins anew, lit by a new Big Bang, its own galaxies rising while ours fades quietly into the background. In a strange way, every theory about the universe's future reflects its beginning. Inflation, which gave rise to the cosmos as we know it, also hints that other universes could still be budding off endlessly. The quantum fluctuations that seeded the first stars remind us that even in apparent emptiness, there is always the potential for something new. And the cosmic microwave background, that ancient whisper from 14 billion years ago, tells us that time itself carries every moment forward, connecting what was to what will be. The end, then, is not something separate from the beginning. It is written into it. The same expansion that gave birth to galaxies is now carrying them away from one another. The same forces that ignited the first stars will one day exhaust the universe of its fuel. Every law of physics that governs what we see today was there in that first instant, already pointing toward the far future. And yet, there is something almost comforting in this. The universe is not rushing toward its end. It moves at a scale so vast that its changes are measured not in years or centuries, but in trillions upon trillions of years. For now, the stars still burn, galaxies still gather in their clusters, black holes still lie in wait at their centres, and life, improbably, exists here in this narrow window of cosmic time when the sky is still full of light. When we look at the beginning, we are not only looking backward, we are looking at the blueprint of everything. We are seeing how the same laws that turned a quantum spark into a universe will one day carry that universe into its final state, whatever that may be. And if there is one lesson hidden in that arc from birth to death, it is this. Nothing in the universe truly stands still. Not stars, not galaxies, not even time itself. The same expansion that carries us away from the Big Bang is carrying us toward whatever comes next. We are part of that motion, part of a story that began long before us, and will continue long after us. And somewhere in that story there may yet be surprises, endings that are not really endings, but doorways to something new. Because if the beginning has taught us anything, it is that the universe is not limited by what we can imagine. It was born from something stranger and grander than we can fully understand. And whatever waits at the end, it may be no less astonishing than the first moment when there was light. And now, after tracing the universe from its first impossible spark to the vast, expanding cosmos we see today, we return, slowly, quietly, to where we are. Not at the edge of the beginning or the horizon of the far future, but here, in this single moment, on a small world, orbiting an ordinary star, beneath a sky that has been burning for nearly 14 billion years. It's strange, isn't it? To realise that everything, the galaxies, the stars, the quiet pull of gravity, the faint glow of the cosmic background, has been leading to this. And yet, in another sense, nothing has been leading anywhere at all. The universe does not plan. It simply unfolds, it expands, it cools, it gives rise to structure, and then, Without ceremony it continues. And in one tiny corner of it, for reasons we still don't fully understand, a part of the cosmos became aware enough to wonder what it is made of. When we look at the night sky, we're not just seeing light. We are seeing time itself stretched across distance. The nearest stars shine at us from years in the past. The faintest galaxies we can detect are sending us light that has travelled for billions of years, crossing nearly the entire history of the universe to reach our eyes. To look outward is to look backward. Every photon is a messenger, and every one of them carries a fragment of the story we have been tracing. A story that began before there were worlds, before there was even the concept of before. And yet, for all the immensity of that story, here we are, in the present, breathing, listening. A part of a universe so vast that it defies comprehension, and yet close enough to touch in the quiet ways that matter most. In the starlight that reaches us, in the gravity that holds us to the earth, in the atoms that were forged in the hearts of long-dead stars and now move through our bodies as we sit beneath this ancient sky. Perhaps that is what makes this journey so extraordinary. The universe is not something separate from us. It is not a distant stage on which we happen to live. It is the reason we are here at all. Every element in our blood, every atom in our bones, every breath we take is part of that same cosmic story. We are not outside observers. We are the universe, looking back on itself and trying to understand. And maybe that's why, even after exploring inflation, dark matter, black holes, and the possibility of infinite universes, we still return to something simple, a moment of quiet, a sense of connection, the recognition that, for all its vastness, the cosmos touches us not only in its size but in its intimacy. Because no matter how far away the beginning might seem, it is written in everything we see and everything we are. There is a kind of peace in that thought. The Big Bang is not gone. It is still happening in its own way, its echoes carried in the light between galaxies, in the slow expansion of space, in the faint cosmic microwave background that surrounds us like a soft memory of the first dawn. To sit here, now, is to be surrounded by that history, to be held within it as if the entire universe were gently cradling the present moment. And when we look up, it's hard not to feel it. Not just the scale, not just the mystery, but the quiet truth that we are, for the briefest flicker of time, a part of this unfolding. We do not need to reach the edge of the universe to touch it. We already live inside it. Every night sky is proof. Maybe that is why, even in the face of so many unanswered questions, what came before, what lies beyond, how it will all end, there is comfort in simply sitting with the fact that we are here now. The universe has been many things, violent in its birth, patient in its growth, incomprehensible in its size. But at this moment, in this small corner of it, it is still enough to pause, to breathe, and to look up. Because if there is anything the beginning has to teach us, it is that the present moment is part of that same grand story. We don't stand apart from the past or the future. We are connected to both. We are made of the same matter that came from the first stars. We are carried forward by the same expansion that began in the first instant. We live in a universe that is still becoming itself, and we are a part of that becoming, whether we realize it or not. So now, as we return from the vast scales of cosmic time, let the silence of space settle around you. Let it be a reminder that even in all this immensity there is room for stillness. The universe has been moving and changing for nearly 14 billion years, but for us right now there is only this. One moment, one world, one sky, and the quiet wonder of knowing that we are part of it. And perhaps that is enough. So, if you are listening as you drift towards sleep, or simply letting your thoughts wander under the faint hum of starlight, take one last glance at the story we've traced. From the first spark in the dark to the birth of stars to galaxies weaving their luminous web to the expansion that carries everything outward still. Then come back here, back to now, to the simple truth that we are the result of all of it, and that even in a universe so endlessly vast, there is something grounding about this single quiet fact. You are here, and the universe, in all its immensity, is here too. And so, as we leave the beginning of everything behind and settle back into this single quiet moment, let your thoughts drift like starlight across a calm sky. The universe will keep expanding, galaxies will keep turning, time will keep flowing. But for now, you are here, and that's enough. Thank you for joining me on this journey through the first spark, the long darkness, and the birth of everything that followed. If you found a little calm here tonight, if this gentle trip across the cosmos has brought you even a moment of quiet wonder, I'd be grateful if you'd leave a like, subscribe, or simply come back the next time you need a place to drift. Sleep well. The universe isn't going anywhere.